Have you ever wondered what it truly means to touch something? Please, take a moment right now. Place your hand on the surface in front of you. Maybe it is the smooth glass of a phone screen, the textured wood of a desk, or the soft fabric of a blanket. Close your eyes and really feel it. You feel a sensation of pressure. You feel a texture. You feel a temperature, perhaps cool or warm against your skin. Your brain tells you that your finger is in direct contact with that object. It tells you that there is no space left between you and the world outside. But this is a lie. It is a beautiful, convincing, and necessary lie that your brain tells you to make sense of reality. But it is a lie nonetheless. The truth is that you have never touched anything in your entire life. You have never touched the hand of a loved one. You have never touched the ground beneath your feet. You have never touched the food you eat or the air you breathe. What you are feeling right now, that sensation of solidity and pressure, is actually a force field. It is the electromagnetic repulsion between the electrons in the atoms of your finger and the electrons in the atoms of the surface. As your finger approaches the table, the electrons, those tiny, mysterious ghosts we are about to investigate, push back against each other with incredible force. The closer they get, the stronger the push. It is like trying to push two powerful magnets together with their north poles facing each other. You feel a resistance. You feel a solid barrier. But they never actually touch. There is always a gap, a tiny, imperceptible abyss of empty space that separates you from everything else in the universe. You're floating, hovering just a few nanometers above the chair you're sitting on, suspended by invisible forces, forever separated from the world by a barrier of electric charge. We live our lives believing in a world of solid objects, of things that bang and crash and hold together. We trust in the solidity of the ground. We trust in the walls of our homes. But if we could shrink down, if we could shed our human scale and descend into the true nature of reality, we would find that solidity is an illusion. We would find that the universe is not made of hard, solid stuff, but of spaciousness, of energy, and of silence. Tonight, I want to take you on a journey into that silence. We are going to leave the world of the big behind. We are going to leave the galaxies and the stars, the planets and the mountains. We are going to descend into the microscopic and then past the microscopic into the subatomic. We are going on a quest to find the smallest thing in the universe. We are going to look for the electron. And the question we are asking seems simple. How big is it? It sounds like a question that should have an easy answer, like, how big is a baseball? Or, how big is the earth? But as we will discover, this question will lead us to the very edge of human understanding. It will force us to question the nature of space, the definition of reality, and the limits of our own minds. But before we can measure the ghost, we must enter its haunted house. Let us begin our descent. Imagine we are looking at your fingertip again. To your eyes, it is just skin, lines and ridges, swirls of a unique fingerprint that has existed only once in the history of time. Now, imagine we have a dial that controls the scale of our vision. We turn the dial. We zoom in. The skin dissolves into a landscape of valleys and hills. We see the dead cells of your epidermis flaking away like tectonic plates on an ancient planet. We see the sweat pores, deep craters releasing moisture into the air. We turn the dial further. The cells become translucent sacs of water and complex machinery. We see the nucleus of the cell, the command center, packed with the twisted ladders of DNA. We are now smaller than a bacterium. We are smaller than a virus. We turn the dial again. The biological machinery fades away. The chaotic dance of chemistry takes over. We see molecules, complex geometric structures of atoms bonded together, vibrating, twisting, and turning. But we must go smaller. We must go deeper. We pick a single molecule. Maybe it is a carbon chain in the oils of your skin. We focus on just one part of it. We are looking for the building block. We are looking for the atom. And here, something strange begins to happen. As we approach the scale of the atom, the noise of the world fades away. The clutter of biology, the structure of chemistry, it all dissolves into a vast, empty silence. We have arrived at the atom. You have probably seen pictures of atoms in textbooks. They usually show a little cluster of red and blue balls in the center, the nucleus, with little yellow balls orbiting around them like planets around a sun. That picture is comforting. It looks like a solar system. It looks like something we can understand. But that picture is wrong. It is not just a simplification. It is a distortion of the true scale of things. If we want to really understand the size of an electron, we have to understand the size of the stage it plays on. We have to understand the emptiness of the atom. Let's build a model in our minds. Let's take a single hydrogen atom, the simplest atom in the universe, and blow it up until it is the size of a great football stadium. Imagine you are standing in the very center of the field. You are looking for the nucleus, the heavy center of the atom where almost all of its mass lives. In our stadium-sized atom, the nucleus would be a marble, a single tiny glass marble sitting on the 50-yard line. That is it. That is the stuff of the atom. Now, look up. Look toward the highest seats in the stands. Look toward the edge of the stadium, hundreds of yards away. That is where the electron is. And what is in between? What fills the space between the marble in the center and the outer seats of the stadium? Nothing. Absolutely nothing. It is not filled with air. It is not filled with water. It is a void more perfect than the deepest vacuum of space between the galaxies. This is the first great shock of the quantum world. Matter is mostly empty space. If you took all the empty space out of the atoms that make up the entire human race, all 8 billion of us, and squash the remaining nuclei and electrons together, the entire population of Earth would fit inside the volume of a single sugar cube. Think about that for a moment. All the history, all the wars, all the love, all the biology, all the complexity of humanity compressed into a sugar cube. And that sugar cube would weigh as much as humanity, billions of pounds, because the mass is still there. But the space, the illusion of size, would be gone. So, here we are, standing in our imaginary stadium. The nucleus is a marble at our feet. The electron is somewhere out there in the nosebleed seats. And now we must ask, if the atom is the stadium, how big is the electron? In our textbook picture, the electron was a little ball, maybe a planet to the nucleus's sun. But if we look for that little ball in the stands, we encounter a problem. If the electron were a ball, we should be able to measure it. We should be able to say, here it is. It is a beach ball. Or, it is a baseball. But when physicists try to measure the size of the electron, they run into a wall of contradictions. If the electron had a physical size, let's say, for the sake of our model, it was a grain of sand orbiting the stadium, it would have to spin. We know electrons have a property called spin. It is fundamental to who they are. But if a grain of sand were spinning with the angular momentum that we measure in an electron, its surface would have to be moving faster than the speed of light. And, as Einstein taught us, nothing can move faster than light. So, The electron cannot be a spinning ball. It cannot be a grain of sand. So, is it smaller? Over the last century, scientists have built larger and larger machines to look for smaller and smaller things. They have smashed particles together at nearly the speed of light to probe the structure of the electron. They found that the proton, the marble in the center of our stadium, is big. It has size. It has parts. It is made of 3 smaller quarks dancing around each other. It is a complex little world of its own. But the electron, every time they looked closer, the electron remained a point, a zero-dimensional speck. But how can something have 0 size? If something has 0 width, 0 height, and 0 depth, does it exist? How can it have mass? How can it carry a charge? If you take a specific amount of electric charge and squeeze it into a space of 0 size, the energy density becomes infinite. The math blows up. The universe should collapse. And yet, here we are. You are sitting there, reading this, your body held together by these impossible, 0-sized ghosts. The light that allows you to see these words is being created by electrons jumping between levels in the atoms of your screen. The thoughts in your brain are electrical impulses carried by ions, orchestrated by the movement of electrons. Everything you are, everything you see, everything you touch, depends on a particle that, according to our best machines, takes up no space at all. This is the paradox we are going to explore. We are going to dive into the heart of this contradiction. We are going to look at the experiments that tried to measure the unmeasurable. We are going to look at the theories that try to explain the inexplicable. We will talk about clouds of probability. We will talk about the vacuum that is not empty. We will talk about strings vibrating in 11 dimensions. But for now, just stay with the image of the stadium. Stand in the silence of that vast, empty space. The marble at your feet, the invisible presence in the stands, and the realization that you and the chair and the earth and the stars are made of this. You are made of silence. You are made of distance. You are made of a vast cathedral-like emptiness, held together by the strong, silent grip of forces we are just beginning to understand. It is a humbling thought, isn't it? We feel so big. We feel so solid. We occupy space. We block the light. But deep down, in the basement of our reality, we are ghosts. We are a collection of points with no dimension, dancing in a void, creating the illusion of a world. As we continue this journey, we are going to try to catch one of these ghosts. We are going to try to pin it down. We are going to ask the universe the question, how small can you get? And the universe, in its gentle, mysterious way, might just answer with a riddle. The journey into the small is not just about measuring distance. It is about understanding the texture of reality itself. It is about peeling back the curtain of the everyday world and seeing the strange, beautiful machinery that hums beneath the surface. So, take a deep breath. Feel the air filling your lungs. Atoms of nitrogen and oxygen, vast stadiums of empty space rushing into your body. Feel the beat of your heart, an electric rhythm driven by the flow of ions, and let yourself relax into the mystery. There is no need to understand it all right now. The confusion is part of the experience. The paradox is part of the beauty. We are just beginning. The door to the subatomic world is open. The silence is waiting for us. Let us step inside. The air is still. The single glass marble, the nucleus, sits motionless on the grass at the 50-yard line, heavy and dense, anchoring our reality. And we are still looking up at the empty stands, searching for that elusive ghost, the electron. In the last chapter, we stripped away the illusion of touch. We stripped away the illusion of solidity. We found that the atom is a cathedral of emptiness. But the human mind struggles with emptiness. We crave structure. We crave familiarity. When we first discovered the architecture of the atom back in the early 20th century, we tried to paint it with the colors of the world we knew. We looked up at the night sky, at the majestic, orderly dance of the planets orbiting the sun, and we thought, as above, so below. It was a beautiful thought. It was a comforting thought. We imagined the atom as a miniature solar system. The nucleus was the sun, a glowing king in the center. The electrons were planets, little distinct spheres of matter whizzing around in perfect, circular orbits. Gravity was replaced by electromagnetism, but the dance was the same. In this view, the size of the electron was just like the size of the Earth. It was a rock. It was a thing with a surface, an equator, a North Pole, and a South Pole. It had a definite location. You could point a finger and say, there it is. It is in section 104, row 12, seat 5. This is the picture that most of us carry in our heads. It is the logo of the atomic age, the 3 crossing loops with dots racing along them. But there is a tragedy in this picture. If you bring the laws of classical physics, the laws that govern baseballs and planets and cars, into our stadium, this beautiful solar system does not survive. In fact, it dies a violent, catastrophic death. Let us play out this scenario. Let us imagine the electron truly as a little ball orbiting the nucleus. In the world of classical electromagnetism, whenever a charged particle moves in a circle, it is accelerating. And when a charged particle accelerates, it screams. It does not scream with sound. It screams with light. It radiates energy. It throws out photons, bleeding away its own momentum into the universe. So, our little planet electron racing around the stadium would begin to glow. It would shine with a desperate, blinding light. And as it shone, it would lose energy. It would slow down. Its orbit would decay. It would not stay in the high seats of the stands. It would begin to spiral inward. It would crash through the lower decks, falling faster and faster, screaming louder and louder, spiraling down toward the marble in the center. The math tells us this death spiral would take less than a fraction of a nanosecond. If the solar system model were true, every atom in the universe would collapse instantly. The electrons would crash into the nuclei. Matter would implode. The universe would vanish in a flash of ultraviolet light. You would not be sitting here. The chair beneath you would not exist. The hand you used to click on this story would be a cloud of neutron soup. But look around you. The world is quiet. The chair is stable. You are still here. The atoms are not screaming. They are silent. They are incredibly, stubbornly stable. They have existed for billions of years, holding their shape, refusing to collapse. This stability is the first great mystery of the quantum world, and it tells us something profound about the size and nature of the electron. It tells us that an electron is not a planet. It is not a little ball moving in a circle. It cannot be. If it were, it would die. So, what is it? To save the universe, to save matter, physicists had to abandon the solar system. They had to dream a new dream. They had to stop thinking of the electron as a thing and start thinking of it as a behavior. Imagine we are back in the stadium, but this time we turn off the lights. It is pitch black. Now, imagine we have a fan, a ceiling fan, hovering over the stadium. It has a single blade, and on the tip of that blade is a glowing blue light. When the fan is off, you see a dot, a single blue point of light. That is the particle. That is the planet. But now we turn the fan on. We crank it up to maximum speed. The blade spins faster and faster. The blue dot moves so quickly that your eye can no longer track it. What do you see now? You do not see a dot. You see a circle. You see a shimmering, glowing blue ring. If you were to reach out and touch that ring, it would feel solid. It would hit your hand, no matter where you touched it along the circle. The particle is effectively everywhere in the circle at once. This is closer to the truth, but even this is too simple. The electron is not just moving fast, it is smearing out. In the 1920s, a French prince named Louis de Broglie asked a question that sounded like poetry, but turned out to be physics. He asked, if light, which we thought was a wave, can act like a particle, can matter, which we think is a particle, act like a wave? What if the electron is not the stone thrown into the pond? What if the electron is the ripple? This changed everything. Suddenly, the size of the electron wasn't the size of a pebble. It was the size of the ripple. Imagine a guitar string. When you pluck it, it vibrates. The wave fills the length of the string. It has a shape. It goes up and down. Now, take that guitar string and bend it into a circle. Connect the ends. If you pluck it now, the wave has to fit perfectly around the circle. The peaks and the valleys have to match up where the ends meet. If they do not, the wave cancels itself out and dies. This is why the electron does not crash into the nucleus. It is not falling. It is vibrating. It is a standing wave wrapped around the nucleus. It can only exist at certain distances, distances where the wave fits perfectly, where the melody resolves. It cannot exist in the space between, just as a guitar string cannot play a note between its harmonics. The orbit became an orbital. And an orbital is not a path. It is a cloud. Let us return to the question of size. How big is the electron? In this new quantum picture, the question shifts. We are no longer asking for the diameter of the hard sphere. We are asking for the size of the cloud. When a hydrogen atom is sitting quietly in its lowest energy state, its ground state, the electron cloud forms a sphere around the nucleus. We call the radius of this cloud the Bohr radius. It is about 0.53 angstroms, or, to put it in our human numbers, it is about 53 picometers. If we go back to our stadium, this cloud would fill the entire space from the marble in the center out to the nosebleed seats. So, is that the answer? Is the electron the size of a stadium? In a way, yes. When the electron is part of an atom, it is smeared out over that entire volume. Its influence, its charge, its presence is distributed like a fine mist throughout that space. It effectively occupies the whole stadium. This is why atoms feel solid. This is why you cannot push your hand through the table. You are not pushing against a tiny speck. You are pushing against a rigid, pressurized cloud of probability. But wait, this feels like a cheat. We said earlier that the electron was a point, a zero-dimensional speck. Now we are saying it is a cloud the size of a stadium. Which is it? If we take the electron out of the atom, if we strip it away and let it float free in the vacuum, does it stay the size of a stadium? Or does it shrink back down to a point? This is where the story gets darker and more confusing. Before we embraced the cloud, back when we were still clinging to classical physics, scientists tried to calculate the size of the electron using pure energy. They thought, okay, the electron has a charge. It takes energy to pack that much charge into a small space. We know that energy and mass are the same thing. Einstein taught us that, with E equals mc squared. So they did a calculation. They asked, how big of a sphere do you need to hold enough electric charge to equal the mass of an electron. They crunched the numbers. They came up with a number, 2.8 femtometers. That is incredibly small. It is trillions of times smaller than a grain of sand. But in the world of the atom, it is actually huge. If the electron were really that big, the proton, which is much heavier, would have to be gigantic. But we know the proton is small. This classical electron radius, as it is called, turned out to be a ghost of a theory that did not work. It was a number derived from a misunderstanding of how mass and charge interact, and yet you will still find this number in textbooks. It is used as a length scale, a ruler for certain equations, but it is not the physical size of the electron. If the electron were a ball of that size, spinning as we know it spins, its surface would still have to move faster than light. The paradox remains. So we have a cloud that acts big and a mass that acts small. We have a particle that seems to have no internal structure, no gears, no wheels, no surface, and yet it carries mass, spin, and charge. It is like finding a box that weighs 10 pounds. But when you measure the box with a ruler, the ruler says 0 inches. How can something be heavy but have no size? To understand this, we have to look at the vacuum again. We have to stop thinking of empty space as empty. We have to descend into the quantum foam. Imagine the surface of the ocean. From a mile up in an airplane, the ocean looks flat. It looks like a smooth blue sheet. But if you jump out of the plane and parachute down, as you get closer, you see that the surface is not smooth. It is churning. It is full of waves. If you get even closer down to the surface itself, you see bubbles, foam, spray, chaos. The vacuum of space is like that ocean. From our giant human perspective, space looks empty and smooth. But if we zoom into the scale of the electron, space becomes a violent, boiling soup, and our lonely electron, our point-like ghost, is not alone. It is surrounded by this foam. It is constantly interacting with this invisible storm. It is pushing on the vacuum, and the vacuum is pushing back. Some physicists believe that what we call the size of the electron might actually be a trick of the light. It might be the size of the disturbance it creates in the vacuum around it. Maybe the electron itself is a true point, a singularity, but it is cloaked in a cloud of virtual particles that it drags around with it like a swarm of bees. When we try to measure the electron, maybe we are just measuring the swarm. We are measuring the shadow it casts on the sea of empty space. So the mystery deepens. We have gone from a planet to a cloud to a point cloaked in a storm. We have traveled from the smooth, orderly orbits of the solar system to the vibrating, musical clouds of the quantum atom. And yet, we still do not have a number we can trust. We still do not have a measurement we can hold in our hands. The electron refuses to sit still for its portrait. As we move into the next chapter, we are going to confront this refusal directly. We are going to look at the uncertainty that is built into the very bones of the universe. We are going to ask Heisenberg why we cannot know everything. And we are going to discover that this fuzziness, this lack of precision, is not a failure of our tools. It is the very thing that allows the universe to exist. If the electron were sharp, if it had a definite edge, the world would freeze. Life requires the blur. Life requires the uncertainty. So let us rest here for a moment. Visualize that shimmering blue cloud filling the stadium. It is not solid, but it is strong. It is not a thing, but it is a presence. It is a ghost that can hold up a skyscraper. It is a ripple that can carry a thought. You are made of these ripples. You are a symphony of standing waves, vibrating in the silence of the void. And the music is just getting started. We are standing on the edge of a precipice. Behind us lies the comfortable world of the large, the world where things have definite shapes and definite places. Ahead of us lies the fog. In the last chapter, we watched the electron dissolve from a planet into a cloud. We watched the hard lines of reality blur into a shimmering haze of probability. But the human mind is stubborn. Even as we accept the cloud, a part of us still whispers, "Yes, but where is it really?" We imagine that if we just had a better microscope, if we just had sharper eyes, if we could just hold the atom still enough, we could peer through the fog and see the little hard seed hidden inside. We believe that the fuzziness is our fault, a failure of our clumsy fingers, a smear on our glasses. We think the electron is like a car driving in the fog. We can't see the car clearly, but we know the car is there. We know it has a bumper, a hood, and 4 wheels. We assume the blur is just a problem with the weather. But in the year 1927, a young German physicist named Werner Heisenberg climbed onto a rock in the middle of the night on a lonely island in the North Sea, and he realized something that shattered this hope forever. He realized that the fog is not the weather. The fog is the car. He realized that the fuzziness is not a mistake. It is the fundamental fabric of existence. This discovery, known as the Heisenberg uncertainty principle, is perhaps the most misunderstood concept in all of science. We often hear it described as a measurement problem. You cannot measure something without disturbing it. Imagine you are in a pitch-black room, trying to find a marble on the floor. You cannot see it. The only way to find it is to touch it. But the moment your finger touches the marble, you push it. You change where it is and how fast it is moving. The act of finding it changes it. This is true, and it is a good metaphor, but it is too simple. It implies that the marble was sitting still before you touched it. It implies that the marble had a definite position, and you just ruined it. Heisenberg went deeper. He said it is not just that we cannot know the position and the momentum of the electron at the same time. He said that the electron does not possess a definite position and a definite momentum at the same time. Think about that. It is not that the information is hidden from us. It is that the information does not exist. The electron is not a point hiding in a cloud. The electron is the cloud. And the nature of a cloud is that it cannot be pinned down to a single point without losing its shape. Let us bring this back to our question of size. How big is the electron? Heisenberg teaches us that size is a trade-off. It is a bargain you make with the universe. Imagine you want to squeeze the electron. You want to compress that stadium-sized cloud down into a tiny box. You want to make it small. You build a trap, an electromagnetic vise, and you start to close the walls. You push the cloud in. You force the electron to occupy a smaller and smaller space. You are effectively measuring its position. You're saying, you are here in this small box. But the universe has a rule. The more precisely you define the position, the smaller you make the box, the more uncertain the momentum becomes. Momentum is energy of motion. If the momentum becomes uncertain, it means the range of possible speeds the electron might have gets wider and wider. It could be moving slowly, or it could be moving infinitely fast. As you squeeze the box, the electron starts to fight back. It starts to vibrate with a frantic, terrified energy. It pushes against the walls of your trap with growing pressure. It is like trying to hold a handful of angry bees. The tighter you squeeze your fist, the more furiously they buzz. If you try to pin the electron down to a single zero-dimensional point, if you try to make its size truly zero, its momentum becomes infinite. It would require infinite energy to hold it there. This is why atoms don't collapse. Remember the death spiral we talked about? The electron crashing into the nucleus? Why doesn't it happen? Why doesn't the negative electron just suck itself onto the positive proton and stick there like a magnet? Because of Heisenberg. If the electron fell into the nucleus, it would be confined to a tiny, tiny space. Its position would be known very precisely. But according to the uncertainty principle, if its position is that precise, its momentum must go wild. The electron would start moving so fast, vibrating with such intensity, that it would effectively kick itself back out. It creates a pressure, a quantum pressure, that balances the pull of the electric charge. The electron stays in the stadium seats, not because it is orbiting, but because it is claustrophobic. It refuses to be confined to the nucleus. It demands space. It demands room to be uncertain. So, in a very real, physical sense, the size of the atom, the vast empty space that makes up your body and the world, is a direct result of the electron's refusal to be small. You are big because your electrons need room to blur. This realization changes how we see the universe. It kills the old idea of the clockwork universe. Before quantum mechanics, scientists believed that if you knew the position and speed of every particle in the universe right now, you could perfectly predict the future forever. The universe was a machine ticking along a set path. But if the particles themselves are fuzzy, if they don't have a definite now, let alone a definite future, then the machine is broken. The future is not written. Chance, probability, and uncertainty are woven into the very building blocks of reality. But we must be careful. We must not get lost in the philosophy and forget our quest. We are still looking for the size of the electron itself, not just the space it occupies in the atom. We know the cloud is big. We know the cloud is necessary. But what happens if we smash the cloud? What happens if we take an electron out of the atom, accelerate it to nearly the speed of light, and slam it into another particle? This is what we do at places like CERN, in the Large Hadron Collider. We use brute force to break the rules of politeness. We don't ask the electron where it is. We force it to reveal itself. And when we do this, when we look at the electron, at these high energies, the cloud disappears. The fuzziness vanishes, and we are left with a point, a single, hard, mathematical point. It is the most maddening thing in physics. When you leave it alone, it is a wave. When you hit it hard, it is a particle. Experiments have probed the electron down to scales of 10 to the power of minus 18 meters. That is 1 billion times smaller than an atom. At that scale, we still see no structure, we see no surface, we see no radius. If the electron were a ball of yarn, we would see the threads. If it were a blob of jelly, we would see it squash, but it behaves like a fundamental, indivisible speck. So, is the answer 0? Is the smallest thing in the universe really nothing more than a coordinate in space? If it is 0, we are back to the problem of infinite density. A point with mass is a black hole. A point with charge has infinite energy. Nature usually hates infinities. Usually when our math gives us an infinity, it means we have made a mistake. It means our theory has broken down. So physicists have had to invent a new way to think about this point. They stopped thinking about stuff and started thinking about fields. Imagine the ocean again. But this time, the ocean fills the entire universe. It is everywhere. It is inside you, outside you, between the stars. We call this the electron field. The field is like a fluid. It is normally calm and flat. But if you flick the surface of this fluid, you create a ripple. a little knot of energy that travels across the ocean. That ripple is the electron. The electron is not a separate thing swimming in the ocean. It is a behavior of the ocean. And what is the size of a ripple? Does a wave on the ocean have a size? You can measure its wavelength, the distance between two peaks. You can measure its height. But can you measure the width of the water that makes it up? The water is continuous. The wave is just a localized excitement. In quantum field theory, the most successful theory in the history of science, particles are just excitations of these universal fields. The electron is a vibration in the electron field. The photon is a vibration in the electromagnetic field. The quark is a vibration in the quark field. When we say the electron is a point particle, what we really mean is that we can't find any smaller parts inside it. You can't cut a ripple in half and get two smaller half ripples. If you cut a ripple, you just mess up the wave. It is fundamental. It is the smallest unit of currency in the electron field. So, the size of the electron depends on how you look at it. If you ask, how much space does it take up in an atom? The answer is a stadium, the cloud. If you ask, what is its internal structure? The answer is 0, the point. If you ask, what is it really? The answer is a ripple in an infinite ocean, the field. This answer, the field, is beautiful. It connects everything. It means that every electron in your body is connected to every electron in the center of the sun and every electron in the most distant galaxy. They are all waves in the same ocean. They are all identical because they are all made of the same stuff, the same field. This is why you can swap one electron for another, and the universe doesn't care. It is like swapping $2 in your bank account. They are just numbers. They are just values in the field. But even this field theory, as powerful as it is, has a problem with gravity. Gravity is the curvature of space and time, and a point particle with mass should curve space infinitely sharply at that point. It should punch a hole in the universe. Quantum field theory works perfectly for everything except gravity. When we try to add gravity to the mix, the math of the point particle explodes. It gives us nonsense. This suggests that our journey is not over. It suggests that the point might be another illusion, just as the solid ball was an illusion and the simple orbit was an illusion. The zero-dimensional point might be a mask hiding something even deeper, something vibrating, something woven from the fabric of dimensions we cannot see. We are approaching the realm of string theory. We are approaching the idea that the electron might be a tiny, tiny rubber band vibrating in a universe of 11 dimensions. But before we go there, we need to sit with the discomfort of the point. We need to feel the weirdness of being made of things that have no size. Look at your hand again. It is a cloud of probability. It is a swarm of uncertain bees buzzing in a cathedral of emptiness. It is a collection of ripples on an invisible ocean that spans the cosmos. And somehow, miraculously, these clouds and ripples and points come together to make skin and bone and nerve. They come together to make the sensation of touch. The repulsion you felt at the beginning of this story, the force field stopping your finger from passing through the table, is the clash of these fields. It is the ocean of your finger crashing against the ocean of the table. The waves push against each other. The clouds refuse to overlap. And in that resistance, in that refusal to merge, the world becomes solid. The electron's stubbornness gives us the ground to stand on. Its uncertainty gives us the space to breathe. Its field gives us connection to the stars. We are walking deeper into the mystery now. The fog is thick, but we are beginning to see patterns in the mist. We have found that reality is not built of bricks. It is built of music. The uncertainty is not chaos. It is the sheet music of the universe, and we are the song. In the next chapter, we will try to break the point open. We will ask if the electron is truly alone, or if it has a family. And we will ask the most dangerous question of all. Could it be that there is only one electron in the whole universe, moving backward and forward in time? The rabbit hole goes deeper. The silence is getting louder. Are you ready to see what lies beneath the point? We have spent the last few chapters descending. We have climbed down the ladder of reality, rung by rung, moving from the human scale of fingertips and tables to the microscopic landscape of cells, then deeper into the cathedral of the atom, and finally to the vibrating, uncertain cloud of the electron itself. We have asked the question, how big is it? And we have received a series of riddles in return. We found a cloud that fills a stadium. We found a point that has no size. We found a ripple in an infinite ocean. But tonight, I want to ask a different question. A question that might seem unrelated at first, but which holds the key to unlocking the deepest secret of the electron's nature. It is a question about identity. It is a question about loneliness. When you look at the world around you, you see a universe of unique things. You see a specific chair. You see a specific tree outside your window. You see a specific person with a specific face and a specific history. Even if you hold two identical apples in your hands, you know they are distinct. One is in your left hand, and one is in your right. One might have a tiny bruise on the bottom. The other might be slightly redder. If you swapped them behind your back, a microscope could tell them apart. They are individuals. They have their own stories. But in the quantum world, this rule of individuality breaks down. It dissolves completely. If you take an electron from the tip of your nose, and you take an electron from the center of a star 1 billion light years away, and you put them next to each other, they are not just similar, they are not just twins. They are mathematically, fundamentally, absolutely identical. There is no this electron or that electron. There is no serial number scratched into their surface. There is no tiny bruise or blemish that distinguishes one from the other. They have exactly the same mass, down to the last decimal point. They have exactly the same charge. They have exactly the same spin. If you were to close your eyes and let me swap them, there is no experiment in the entire universe, no machine, no God, no mathematical trick that could tell you I had made the switch. This is known as the principle of indistinguishability. And while it sounds like a technical curiosity, it is actually one of the most haunting mysteries in physics. Why should they be the same? Think about the sheer size of the universe. Think about the violence of the Big Bang, the chaos of exploding stars, the silence of the intergalactic void. Electrons have been forged in different fires, traveled different paths, existed for billions of years in completely different environments. And yet, every single one of them, every single one of the 10, followed by 80 zeros of them in the visible universe, is a perfect, flawless copy of every other one. It is as if every car on Earth, from the rusted truck in a field to the luxury sedan in a showroom, was not just the same model, but the exact same car, down to the atomic arrangement of the rust. This perfect sameness bothered the great physicists of the 20th century. It felt unnatural. In a universe of chaos and diversity, such perfect order demanded an explanation. And in the spring of 1940, a legendary phone call took place that offered an explanation so wild, so beautiful, and so terrifying that it sounds more like science fiction than science. The call was between John Wheeler, a physicist known for his deep, poetic mind, and his student, Richard Feynman, who would go on to become one of the most famous scientists in history. Wheeler was excited. He shouted into the phone, "Feynman, I know why all electrons have the same charge and the same mass." Feynman asked, "Why?" And Wheeler replied, "Because they are all the same electron." Let that sink in for a moment. Wheeler was suggesting that there are not trillions and trillions of electrons in the universe. He was proposing that there is only one single solitary electron. But how could one electron be in your finger and in the sun and in the Andromeda galaxy all at the same time? To understand this, we have to stop thinking of time as a flowing river that carries us from the past to the future. We have to think of time as a dimension, just like space. We have to look at the whole tapestry of space-time at once. Imagine the life of a single electron as a long piece of thread. It starts at the beginning of time. It moves forward through history. It enters a cloud of gas. It becomes part of a star. It floats in deep space. But then, Wheeler suggested, imagine that this thread doesn't just go forward. Imagine it can bend. Imagine it can loop. Suppose this single electron traveling through the universe hits a point where it turns around. It makes a U-turn in time. It starts traveling backward from the future into the past. Then, millions of years in the past, it turns around again. It loops back toward the future. It does this again and again. It creates a massive, tangled knot of thread that fills the entire volume of space-time. It weaves back and forth, up and down, past and future, billions and trillions of times. Now imagine we take a slice of this knot. Imagine we take a knife and cut through the tangle at a specific moment in time. Let's say, now. What would we see on the face of the cut? We would see millions of little points where the thread passes through our slice. Half of those points would correspond to the thread moving forward in time. We would call these electrons. The other half would correspond to the thread moving backward in time. What does an electron moving backward in time look like to us? It looks like a particle with the same mass, but opposite charge. It looks like the mirror image of an electron. We call it a positron. We call it antimatter. This was Wheeler's grand idea, the one-electron universe. He proposed that every electron in your body and every electron in the universe is just a different segment of the same single eternal line, passing through our moment in time again and again and again. We are not made of billions of particles. We are made of one thread, woven so tightly and so complexly that it creates the illusion of a solid reality. We are a tapestry woven from a single strand of light. When Feynman heard this idea, he laughed. He immediately saw a problem. He said, "But, Professor, there aren't as many positrons as electrons. If the thread loops back and forth for every section moving forward, there should be a section moving backward. For every electron, there should be a positron. The universe should be half matter and half antimatter. But we look around, and we see almost only matter. The positrons are rare. They are hidden in cosmic rays and particle accelerators. They are not part of our daily lives." Wheeler, with his characteristic imagination, replied that perhaps the positrons are hiding in the protons, or perhaps the other parts of the thread are simply somewhere else, visible only to a mind that can see the whole picture. The theory was never fully accepted as a literal truth. It remains a what-if, a beautiful mathematical curiosity. But like all great myths, it points to a deeper truth. Even if there isn't just one physical electron looping through time, quantum field theory, the theory we discussed in the last chapter, tells us something very similar. It tells us that there is only one electron field. There is only one ocean, whether it is one particle weaving back and forth or one field vibrating in a trillion places. The conclusion is the same. Separation is an illusion. The you that sits there reading this is not separate from the me that is writing it. We are excitations of the same field. We are knots in the same thread. And this brings us back to the question of size. If the electron is really a thread that weaves through the entire history of the universe, does it make sense to ask how big it is? Is the size of the thread the width of the string, or is it the length of the tapestry? If the electron is a traveler that has visited every corner of the cosmos, then, in a way, its size is the size of the universe itself. It is a thread that stitches the galaxies together. This idea of the world line, the path of a particle through space-time, gives us a new way to visualize the subatomic world. We stop seeing little balls bouncing around. We start seeing a four-dimensional sculpture. Imagine a static block of ice. Inside the ice, there are threads frozen in place. The block is the universe. The threads are the particles. Nothing is moving. The motion is an illusion created by our consciousness sliding up the block, slice by slice, moment by moment. In this block, the electron is a long, thin filament. It is a structure that stretches from the Big Bang to the end of time. It is ancient. It is infinite in its own way. When you touch your finger to the table, you are bringing your bundle of filaments close to the table's bundle of filaments. They do not touch. They just weave close to each other, their fields interacting, their histories intertwining for a brief moment before separating again. This perspective is dizzying. It makes us feel small, but it also makes us feel vast. It reminds us that we are not just creatures of the moment. We are structures of deep time. The electrons in your hand have a history that goes back 13.8 billion years. They have seen the birth of stars. They have drifted in the cold dark between galaxies. They might have been part of a dinosaur's breath or a drop of rain on a primordial ocean. And long after you are gone, long after the earth is gone, they will continue. They will carry the memory of your existence, the subtle changes in their quantum state, the tiny shifts in their path. Into the deep future, you are a pattern carried by immortal travelers. This is the comfort of physics. It takes away our ego, our sense of being the center of the world, but it gives us back a connection to everything else. We are not isolated. We are not alone. We are woven into the same fabric. As we move deeper into this night, we need to confront another aspect of the electron's identity. We have talked about its size, its cloud, its indistinguishability, but we have not talked about its spin. The electron is not just a point. It is not just a cloud. It is not just a thread. It is a dancer. It is pirouetting in the dark, spinning with a momentum that cannot be stopped. But this spin is not like the spin of a top. It is something stranger, something that defies our geometry. If you turn a top 360 degrees, it comes back to where it started. It looks the same. But if you turn an electron 360 degrees, it looks different. It has changed. To make an electron look the same again, you have to turn it 720 degrees. You have to turn it twice. What kind of object needs to be turned twice to get back to the start? What kind of geometry allows for that? It is as if the electron is attached to the universe by a ribbon, and turning it once puts a twist in the ribbon. You have to turn it again to undo the twist. In the next chapter, we will try to visualize this dance. We will try to understand this spin that gives the electron its magnetism and gives matter its structure. We will see that the electron is not just a passive ghost. It is a little engine of orientation. It is a compass needle pointing to a direction that doesn't exist in our 3 dimensions. But for now, let us rest with the image of the single thread. Close your eyes again. Visualize the darkness of space. Visualize a single glowing line of light, zipping back and forth, faster than thought, weaving a complex, glowing knot. Visualize that knot becoming denser and denser until it forms the shape of a galaxy, until it forms the shape of a star, until it forms the shape of a planet, until it forms the shape of you. You are a knot of light in the fabric of space-time. You are a single note in a song that has been playing forever. You are the universe, weaving itself into existence, one electron at a time. And in the silence of that realization, the question of size begins to fade, replaced by a feeling of profound, quiet wonder. We are the mystery we are trying to solve. We are now deep inside the machine. We have moved past the empty stadium, past the shimmering cloud, and past the tangled thread of time. We have arrived at the property that gives the electron its personality, its stubbornness, and ultimately its power to build the world. We have arrived at the mystery of spin. In the last chapter, I left you with a riddle. What kind of object must be turned around twice to return to where it started? If you pick up a book and rotate it 360 degrees, the cover faces you again. If you walk in a circle, you end up looking at the same view. In our daily life, a full circle is the end of the journey. 360 degrees is home. But the electron lives in a different geometry. If you could mark the front of an electron and spin it 360 degrees, it would not look the same. It would be in a state that is mathematically negative to its starting point. It is facing anti-front. To get it back to its true original state, you have to spin it another 360 degrees, 720 degrees in total. This sounds like nonsense. It sounds like a breakdown of logic. But there is a way to feel it in your own body. Try this. Hold a cup of water in the palm of your hand. Now, without spilling it, try to rotate your hand a full circle. You have to twist your arm, tucking your elbow in. When your hand has made a full circle, your arm is twisted. You are in a stressed state. You are not back to normal, even though your palm is facing up again. To untwist your arm without spilling the water, you have to keep rotating your hand in the same direction for another full circle. Your elbow swings over, your shoulder rolls, and finally, after 2 full rotations, your arm is straight again. The electron is like that cup of water. It is tethered to the fabric of space-time in a way that requires this double rotation to untangle. This property is what physicists call spin 1-2, but we must be very careful with the word spin. When we say a top spins, we mean the material of the top is moving around an axis. We mean that if we touched the side of the top, it would burn our finger with friction. The electron is not spinning like that. Remember, the electron is a point. It has no radius. It has no surface. If a point spins, what is moving? Nothing is moving. And yet, it has angular momentum. It behaves exactly as if it were a tiny spinning magnet. If you shoot an electron through a magnetic field, it will deflect. It will curve either up or down, depending on its spin. It acts like a tiny compass needle. So we have an object that is not rotating, yet has rotation. An object that has no size, yet has a north pole and a south pole. Physicists call this intrinsic angular momentum. It means that spin is not something the electron does. It is something the electron is. An electron doesn't have spin any more than a photon has speed. A photon is speed. An electron is spin. If you stopped it from spinning, it would cease to be an electron. This intrinsic spin is the engine of the atom. It is the secret architect of the periodic table. And it leads us to the most important rule in the universe for understanding why matter takes up space. It leads us to the Pauli exclusion principle. This is where the story of size finally clicks into place. We asked, how big is the electron? And we found that the electron is a tiny ghost that wants to be everywhere at once. But we also know that matter is rigid. We know that stone is hard. We know that water cannot be compressed easily. If atoms are mostly empty space and electrons are just ghostly clouds, why doesn't matter just pass through other matter? Why can't we stack 1,000 electrons in the same spot? The answer lies in the spin. The first family is the bosons. These are the particles of force and light, like the photon. They have whole number spins, 0, 1, 2. Bosons are social. They love to be together. You can pack 1 trillion photons into the same tiny box, all in the same state, all singing the same note. This is how a laser works. Billions of photons marching in perfect lockstep. The second family is the fermions. These are the particles of matter, the electron, the proton, the neutron. They have half-integer spins, 1, 2, 3, and 2. And fermions are antisocial. They are the rugged individualists of the cosmos. Wolfgang Pauli, an Austrian physicist with a famously sharp tongue, discovered a law that governs these antisocial ghosts. The law says simply, no two fermions can occupy the exact same quantum state at the same time. They cannot be in the same place, with the same energy and the same spin. If one electron is sitting in the lowest energy seat of the stadium, the ground state, and it has its spin pointing up, another electron can come and sit in that same seat, only if its spin is pointing down. They can share the seat if they face opposite directions. They become a pair. But what if a third electron comes along? It tries to sit in the lowest seat, but the seat is full. There is an up electron and a down electron. There is no room for a third. So the third electron is forced to move. It cannot sit in the best seat. It has to go to a higher row in the stands. It has to take a seat with more energy, further away from the nucleus. Then a fourth electron comes. It takes the down spin seat in that second row. Then a fifth comes. It has to go even higher. This is the exclusion principle. This is the architecture of the void. Because electrons refuse to overlap, they are forced to stack up. They build shells around the nucleus, layer upon layer. Imagine a hotel where every room has only 2 beds. Once the first floor is full, new guests must go to the second floor. Once the second is full, they must go to the third. This stacking is what gives the atom its volume. If electrons were bosons, if they didn't have this specific spin 1-2 nature, they would all crash down into the lowest energy level. They would all huddle together in the bottom bunk. If that happened, every atom would be tiny. Chemistry would not exist. There would be no bonding, no structures, no life. The entire universe would be a soup of super-dense, boring lumps. But because electrons are fermions, because they demand their own space, the atom puffs up. It grows. The size of an atom, that stadium-sized cloud we talked about, is actually a manifestation of the electron's need for personal space. The cloud is not just one electron running around. In larger atoms, it is a complex structure of many electrons avoiding each other, carving out their own territories in the vacuum. And this brings us back to your finger on the table. We said in the first chapter that you feel a force field. We said it was electromagnetic repulsion. That is true, but it is only half the story. The deeper truth is that you are feeling the Pauli exclusion principle. As the electrons in your finger get close to the electrons in the table, the clouds start to overlap. But the electrons in the table are already happy. They are in their specific states. They are full. The electrons in your finger are intruders. They try to occupy the same space. But the universe says no. The exclusion principle acts like a force. It is called degeneracy pressure. It is not a force like gravity or electromagnetism, which travel across space. It is a rule of existence. It is a command written into the logic of reality. The universe effectively says, you cannot be here because I am already here. And so, to avoid violating this law, the electrons in your finger and the table push back with tremendous energy. They resist compression. That resistance, that stubborn, absolute refusal to merge, is what you call touch. It is what holds up the floor. It is what keeps the stars from collapsing. When a massive star runs out of fuel and tries to implode under its own gravity, it is the degeneracy pressure of electrons that fights back. It creates a white dwarf star, a diamond the size of the Earth, held up entirely by the electron's refusal to surrender its space. So, the size of the electron is, in a way, the power of its identity. It is small, a point, but its influence is vast, because it defends its territory with the strength of a fundamental law. This dance of spin and exclusion is also what makes magnetism possible. Remember that each electron is a tiny magnet. In most materials, the electrons are paired up, one down. Their spins cancel out. The magnetism disappears. But in some materials, like iron, the electrons in the outer rows of the stadium get lonely. They don't have partners, and something strange happens. They talk to their neighbors. They align. Billions of lonely electrons, all spinning in the same direction, all pointing their north poles the same way. Their tiny microscopic magnetic fields add up. They amplify each other. And suddenly, the stone comes alive. It can pull a nail across a table. It can point to the north. The invisible geometry of spin reaches up from the subatomic basement and grabs the world of the big. It is beautiful, isn't it? The solidity of the ground, the touch of a hand, the needle of a compass. All of these solid, tangible things are emergent properties of a ghostly spinning point that takes up no space and must be turned twice to see the world straight. But there is a shadow in this dance. We have talked about the electron as a stable, eternal partner. We have talked about it building the shells of atoms, but we have not talked about where it gets its mass. Why does it have mass at all? Why is it heavy? For a long time, we thought mass was just a property that things had, like color or shape. But in the modern view of the universe, mass is not a property. Mass is an interaction. Mass is a drag. Imagine walking through a field of deep snow. It is hard to move. You feel heavy. You feel slow. Now imagine walking on ice. You slide. You are light. The universe is filled with a field, another field, different from the electron field. It is called the Higgs field. And the electron, as it dances its spin 1-2 pirouette, is wading through this Higgs snow. It is constantly bumping into the Higgs field, interacting with it, getting bogged down. This interaction is what we call mass. If we could turn off the Higgs field, the electron would lose its mass. It would become weightless. It would instantly accelerate to the speed of light. The atom would fly apart. The electron would no longer be able to orbit the nucleus. The stadium would dissolve. So, the size of the electron and the size of the atom depend on this drag. They depend on this constant friction with the invisible snow of the universe. We are uncovering a picture of reality where nothing is what it seems. Solidity is exclusion. Mass is drag. Structure is a standing wave, and the electron is the protagonist in all of these stories. It is the weaver, the dancer, the builder. But there is one final layer to this onion, one final uncomfortable question that Heisenberg hinted at, but which we haven't fully faced. We have been talking about the electron as if it exists when we are not looking at it. We have been using words like cloud and field and spin to describe what it is doing in the dark, but quantum mechanics has a darker secret. It suggests that until we look, until we measure, until we interact, the electron might not be anything at all. It might be just a list of possibilities, a ghost of potential. Does the electron have a size before we measure it? Or does the act of measuring create the size? In the next chapter, we are going to walk into the laboratory of the mind. We are going to meet Schrodinger's cat, and we are going to ask the electron, are you real? We will explore the observer effect and the terrifying possibility that consciousness itself might be woven into the process of defining reality. The silence is deep now. The dance of the spin is dizzying. Take a breath. Feel the solidity of the chair, the Pauli exclusion principle holding you up. Feel the weight of your body, the Higgs field pulling on your electrons. And prepare to question the existence of the world itself. We have arrived at the threshold of the mirror. So far, our journey has been physical. We have talked about forces, about clouds, about vibrations, about spin. We have treated the electron as a tiny actor on a vast stage, an actor who might be fuzzy or shy, or spinning in two directions at once, but an actor who is definitely there, waiting in the wings even when the spotlight is turned off. But now, the ground beneath our feet begins to dissolve. We are about to enter the most vertigo-inducing room in the quantum mansion. We are going to ask a question that sounds like it belongs in a philosophy seminar, or a dream, but which is actually the most urgent question in physics. Does the electron exist before we look at it? This is not a trick question. It is the question that kept Albert Einstein awake at night. It is the question that drove Erwin Schrodinger to invent a zombie cat. And it is the question that suggests that you, yes, you, the observer, are not just watching the universe, but are actively stitching it together with your gaze. Let us go back to our stadium. Imagine we are sitting in the press box high above the field. We know there is an electron somewhere in the stadium. We know it is a wave, a cloud of probability. But let's say we want to find it. We want to pinpoint it. We set up a trap. We place a detector, a tiny, high-tech camera, at every single seat in the stadium. 50,000 cameras, all pointed at 50,000 seats, all waiting to catch the ghost. We turn the cameras on. Click. Instantly, one camera, and only one camera, flashes. It captures the electron sitting in section 105, row A, seat 3. At that exact moment, something magical and violent happens. The cloud vanishes. The wave disappears. The probability, which was spread out over the entire stadium a billionth of a second ago, instantly collapses into a single point. The electron is no longer everywhere. It is here. But here is the mystery. Where was it right before the camera clicked? Was it already in seat 3, hiding in the dark, waiting to be found? Was it like a misplaced set of keys that is always somewhere, even if you don't know where? The math of quantum mechanics gives us a startling answer. No. Before the measurement, the electron was not in seat 3. It was not in seat 4. It was not in any seat. It was in a state of superposition. It was a complex, shimmering, mathematical ghost that was partially in every seat at once. It was a wave of potentiality, not a particle of reality. The act of looking, the act of measurement, did not just reveal the electron. It forced the electron to decide where to be. This is the Copenhagen interpretation. It says that the unobserved world is a landscape of ghosts. It says that size and position are not attributes that belong to the electron, like the color belongs to a car. They are attributes that are created in the transaction between the observer and the observed. This is where the size of the electron becomes truly slippery. Before you look, the size of the electron is the size of its wave function. It can be small or it can be huge. If you let an electron float in deep space, its wave function will spread out over thousands of miles. It will become a cloud the size of a planet. But the moment a photon of light hits it, the moment the universe asks, "Where are you?" it snaps down to a point. It goes from being a planet-sized ghost to a zero-dimensional speck in zero time. This instantaneous collapse is what bothered Einstein. He hated it. He famously asked a friend, walking home from a seminar, "Do you really believe the moon is not there when you're not looking at it?" It sounds absurd. Of course the moon is there. It is big. It is heavy. But the moon is made of atoms, and atoms are made of electrons, and electrons are ghosts. So, at what point does the ghost become a rock? At what point does the cloud become a cat? This brings us to the famous thought experiment, Schrödinger's cat. Erwin Schrödinger was actually trying to show how ridiculous this idea was. He said, imagine a sealed box. Inside, there is a cat. There is also a tiny bit of radioactive material, a Geiger counter, and a vial of poison. The radioactive atom is in a superposition. It is unstable. According to quantum mechanics, after 1 hour, the atom is both decayed and not decayed at the same time. It is a wave of two possibilities. If it decays, the Geiger counter clicks, a hammer drops, the poison is released, and the cat dies. If it does not decay, the cat lives. But because the atom is both decayed and not decayed, the entire system enters a superposition. Until you open the box, the math says the cat is not dead. It is not alive. It is a wave function of dead alive. It is a smear of reality. Schrödinger thought this was absurd. A cat is a living, breathing creature, not a quantum ripple. A cat is either alive or dead, regardless of whether a physicist opens a box. But experiments over the last century have shown that Schrödinger's sarcasm backfired. The universe really does work this way. We can't do it with cats yet, but we have done it with molecules. We have taken large molecules, buckyballs made of 60 carbon atoms, and put them in two places at once. We have forced them to be ghosts. So, the boundary between the quantum world of the small and the classical world of the big is not a sharp line. It is a blur. The size of reality depends on how isolated you are. If you can isolate an object from the rest of the universe, if you can stop the air molecules from hitting it, stop the photons from bouncing off it, it will dissolve into a wave. It will lose its definite size and position. The reason you and I feel solid, the reason the moon stays in the sky, is because we are constantly being observed, not necessarily by eyes, but by the environment. The air molecules hitting your skin are measuring you. The light from the lamp is measuring the chair. The cosmic microwave background radiation is measuring the moon. This constant bombardment forces our wave functions to collapse over and over again, trillions of times a second. It freezes us in place. It gives us a definite size. We are like frames in a movie, flashing so fast it looks like continuous motion. But in the tiny gaps between the air molecules, for the briefest fractions of a second, we might just be dissolving back into the cloud. This idea changes how we feel about the electron. It is not just a building block. It is a question mark. It is a packet of potential waiting for an invitation to exist. And it leads to an even stranger possibility, one that takes the size of the electron and stretches it across infinite universes. There is another interpretation, a rival to the Copenhagen view. It is called the many worlds interpretation. It says that the wave function never collapses. It says that the electron never chooses a seat. Instead, the universe splits. In our stadium experiment, when the camera clicks, the universe divides into 50,000 separate branches. In one universe, you see the electron in seat 1. In another universe, a different version of you sees it in seat 2. In another, seat 3. Every possible outcome happens. Every possible size is realized. In this view, the size of the electron is truly infinite. It occupies every possible position in a multiverse of endless branching realities. You are living in just one slice of a much larger, much stranger cake. The electrons in your body are anchoring you to this specific timeline, this specific version of history. But in the shadow worlds next door, they are doing something else. This sounds like fiction, but the math for many worlds is actually cleaner than the math for Copenhagen. It doesn't require a magical collapse. It just requires an infinite number of universes. Whether you believe in the collapse or the multiverse, the lesson is the same. The electron is not a simple object. It is a gateway. It is the interface between the void of possibility and the solidity of fact. And size is just the shadow that potential casts when it enters our world. Let us return to the silence of the room you're in. Look at the walls. They seem static. They seem to be standing still, enclosing a definite volume of air. But now, you know the truth. Those walls are a seething ocean of wave functions. The electrons in the paint are vibrating in superpositions, smelling out all the possible paths, until the light from your lamp hits them and forces them to say, I am here. The world is not a painted picture. It is a painting being painted continuously forever by the interaction of everything with everything else. And you are part of the brush. Your presence, your body, your temperature, your gravity. You are interacting with the room. You are collapsing the waves around you just by existing. You are walking through a fog of ghosts, and your passage solidifies them into a world. This brings a profound intimacy to our relationship with the electron. It is not an alien speck. It is a partner. It waits for you. But there is one more twist in this relationship. One more way that the electron mocks our concept of space and size. We have talked about the electron being here or there. We have talked about it being a cloud or a point. But what if two electrons, separated by the entire width of the universe, are actually the same object? What if space itself is an illusion that the electron can ignore? We are approaching the phenomenon that Einstein called spooky action at a distance. We are approaching entanglement. If spin was the dance and superposition was the ghost, then entanglement is the telepathy. It is the final nail in the coffin of size as a local concept. If two particles can communicate instantly across 1 billion light years, does the distance between them mean anything? If an electron in your eye is entangled with an electron in a black hole at the center of the galaxy, are they really two separate things? Or are they two ends of a wormhole that bypasses the map of the universe? The size of an entangled system is not measured in meters. It is measured in connection. As we prepare for the next chapter, let yourself feel this connection. Feel the fact that the boundaries of your body are not as sharp as you thought. You are a cloud of probability collapsing into a solid form. You are a ripple in a field that spans the stars. And you are an observer standing in the center of a storm of potential, collapsing the chaos into order with every beat of your heart. The electron is not just the smallest thing in the universe. It is the clay from which reality is sculpted, and the sculpting is never finished. We are about to step out of the isolated laboratory and into the cosmic web. We are about to see how these lonely, fuzzy, spinning points hold hands across the dark. We are about to find out that in a quantum universe, no one is ever truly alone. The silence is waiting. The connection is humming. Are you ready to pull the thread and see what moves at the other end of the universe? We have walked through the valley of the atom. We have climbed the mountain of the probability cloud. We have stared into the mirror of the observer and watched reality dissolve into a mist of potential. But now, we must cross the bridge. We are leaving the solitary world of the single electron. We are leaving the lonely ghost spinning in the dark. We are about to discover that in the quantum universe, loneliness is perhaps the greatest illusion of all. We are about to enter the realm of the impossible connection. Tonight, we are going to talk about love, not the chemical love of biology, nor the emotional love of poets, but the fundamental, structural love of the physical universe. We are going to talk about a bond so strong, so ancient, and so absolute that it ignores the laws of space and time. We are going to talk about entanglement. And in doing so, we will shatter the very last definition we have of size, because if two things can touch each other across the width of the universe without ever crossing the space between them, then what does distance actually mean? Let us go back to our laboratory of the mind. Imagine we have a machine. It is a simple machine, a crystal that takes a single photon of high energy, a particle of ultraviolet light, and splits it. This is a common process in physics. It is called spontaneous parametric down conversion. The single photon dies, and in its place, two red photons are born. These two red photons are twins. They are born from the same event at the same nanosecond, from the same parent energy. Because of the laws of conservation, the strict accounting rules of the universe, these twins are linked. If the parent had zero spin, the twins must have opposite spins to cancel each other out. If one spins up, the other must spin down. The total must always be zero. Now let us take these twins and separate them. We carefully capture them in fiber optic cables. We send one, let's call it photon A, to a laboratory in New York. We send the other, photon B, to a laboratory in Tokyo. They are separated by thousands of miles. They are oceans apart. According to our classical intuition, the intuition of baseballs and cars, these photons are now two separate objects. They are like a pair of gloves. If I put the left glove in a box and send it to New York, and the right glove in a box and send it to Tokyo, the fact that they are a pair doesn't change anything about their physical reality. The left glove is in New York. It is a left glove. It has been a left glove ever since I packed the box. The distance doesn't matter. But quantum mechanics is not about gloves. It is about coins that are still spinning. Remember what we learned in the last chapter? Until we measure a particle, it is not in a definite state. It is a cloud. It is a superposition. So, photon A in New York is not spin up or spin down. It is a spinning coin. It is a blur of both possibilities. And photon B in Tokyo is also a spinning coin, a blur. But here is the magic. Here is the spooky action that terrified Einstein. The coins are not spinning independently. They are spinning together. They are a single wave function that happens to be stretched across the planet. Now, imagine an observer in New York, let's call her Alice, decides to look. She sets up her detector. She catches photon A. The camera clicks. The wave function collapses. The coin stops spinning. Let's say Alice measures spin up. At that exact instant, at the precise moment, Alice's detector registers the hit. Something miraculous happens in Tokyo. Photon B, which was happily spinning in a superposition of up and down, suddenly stops. It collapses, and it collapses into spin down. It doesn't send a radio signal. It doesn't send a text message. It doesn't scream across the ocean. It just knows. And it knows instantly. Faster than the speed of light. Faster than time. If Alice measured up, Bob in Tokyo must measure down. If Alice measured down, Bob must measure up. They are perfectly correlated. Einstein hated this. He hated it with a passion that drove him to write one of the most famous papers in the history of physics, the EPR paradox. He argued that this instant connection violated the speed limit of the universe. Nothing can travel faster than light, he said. Therefore, the particles cannot be communicating. He proposed a different solution. He said, it's the gloves. He argued that the particles were never really spinning coins. He said they had a hidden plan all along. When they were born in the crystal, they secretly agreed. I will be up and you will be down. We just didn't know it until we looked. He called this hidden variables. It was a sensible, logical, comfortable idea. It saved the universe from magic. It saved the universe from ghosts. But the universe, as we have learned, does not care about our comfort. In the 1960s, an Irish physicist named John Bell came up with a way to test this. He figured out a mathematical inequality, a test, that could prove whether the particles were gloves, hidden variables, or magic coins, entanglement. We have done the test. We have done it again and again with better and better technology. We have done it across cities, across islands, and even up to satellites in orbit. And every single time, Einstein was wrong. The particles do not have a hidden plan. They are truly undecided until the moment of measurement, and yet they coordinate perfectly. This means that the separation between New York and Tokyo is, in a very deep sense, an illusion. For the entangled pair, the thousands of miles of ocean, the curvature of the earth, the clouds, the cities, none of it exists. They are not two particles separated by space. They are one single object that happens to manifest in two places at once. So, let us ask our question again. How big is the electron? If you take two entangled electrons and separate them by 1 billion light-years, one in the Milky Way, one in a distant quasar, they are still one system. They are a single entity. Does that mean the electron is 1 billion light-years wide? In a way, yes. The quantum state, the mathematical soul of the particle, occupies that vast volume. The size of the system is the size of the separation. This shatters our idea of locality. We tend to think that things are only influenced by what is touching them. You get pushed if someone touches you. You get wet if the rain hits you. But entanglement suggests a universe where touching is obsolete. It suggests a universe that is non-local, a universe where everything is connected to everything else through invisible, instantaneous threads of shared history. Think about the Big Bang. 13.8 billion years ago, all the matter in the universe was compressed into a point smaller than an atom. Every electron, every proton, every neutron was touching every other particle. They were all entangled. They were all part of the same burning, primordial soup. Then the universe exploded, It expanded. It flew apart. The particles drifted away from each other. They formed hydrogen clouds. They formed stars. They formed galaxies. They formed the carbon in your skin and the iron in your blood. But have they forgotten each other? If entanglement is a permanent bond, then in some deep quantum way, every particle in your body might still be entangled with particles billions of light years away at the edge of the observable universe. You are not just a collection of atoms here in this room. You are a node in a cosmic web. When an electron in your brain shifts its state to form a thought, does a partner electron in the Andromeda galaxy quiver in response? The physicists are careful here. They warn us not to go too far. They tell us about the no communication theorem. They tell us that while the connection is instant, we cannot use it to send messages. We cannot use entanglement to send a faster-than-light Morse code. Alice in New York sees a random result, up or down. She can't control it. She can't force her electron to be up so that Bob's will be down. She just sees a random flip. Bob sees a random flip too. Only when they meet up later, when they compare their notebooks, do they realize that their random flips matched perfectly. So, nature protects her speed limit. No information travels faster than light. Only the correlation. But the philosophical implication remains. The connection is real. The universe is not a collection of separate objects sitting in an empty void. The universe is a single, seamless blanket. When you pull on a thread here, the fabric moves there. This view of reality, this holistic view, is perhaps the most beautiful gift of quantum mechanics. It heals the wound of separation that we discussed in the first chapter. Remember how we said, you can never touch anything? That the repulsion of fields keeps you isolated. That is the story of the fermion, the antisocial particle. But entanglement is the counter-story. It is the story of the bond that cannot be broken. It tells us that while our bodies might be separate, our quantum history is one. The space between us is not empty. It is woven thick with these invisible threads. Now, let us descend even deeper. Let us look at what this means for the vacuum itself. If particles can pop into existence, become entangled, and then separate, and if the vacuum is filled with quantum foam, then the empty space you are looking at, the space between your eyes and this screen, is seething with temporary entanglements. Virtual particles are born in pairs. An electron and a positron appear out of nothing, borrow energy from the vacuum, look at each other, entangle, and then crash back together and vanish. They live for a trillionth of a nanosecond. But in that brief life, they weave the fabric of space. Some physicists, like Leonard Susskind, have proposed an idea called ER hoc EPR. It is an equation that links Einstein's gravity, ER bridges or wormholes, with quantum mechanics, EPR entanglement. It suggests that entanglement creates space. It suggests that the reason space holds together, the reason there is a distance at all, is because of these billions of tiny, stitching threads of entanglement. If you cut the entanglement, space would fall apart. The universe would disintegrate into a disconnected dust of points. So, the electron is not just a player on the stage. By entangling with its neighbors, it is knitting the stage itself. It is a spider spinning the web of reality. How big is the electron? It is the size of the web it spins. And since the web is everywhere, the electron is everywhere. We are getting closer to a final realization, a realization that size is the wrong question entirely. Asking how big is an electron is like asking how much does the color blue weigh, or how long is a melody. It is a category error. The electron is not a thing that has size. It is a process. It is a relationship. It is a verb, not a noun. It electrons. It vibrates. It spins. It clouds. It entangles. As we move toward the final chapters of our journey, we are going to look at what happens when we try to stop the dance. We are going to ask, what happens if we freeze time? What happens if we take away the energy, the heat, the movement? We are going to descend into the absolute cold, into the Bose-Einstein condensate. In that frozen world, individual atoms lose their identity completely. They merge. They become a single, giant super atom, a giant quantum ghost that you can actually see with your naked eye. We will see the electron surrender its individuality entirely and become part of a collective soul. But for now, stay with the feeling of the thread. Look at the stars outside your window, or imagine them if it is day. Pick one star, any star. Know that there is a physical quantum link between the atoms in your retina and the atoms in that star. The light that hit your eye created a chain of entanglements that connects you to that fusion reactor burning in the deep dark. You are touching the star. You are touching the edge of the universe. The silence of space is not a silence of emptiness. It is the silence of a held breath, a tension of infinite connections humming in the dark. We are all one thing, pretending to be many. We are the single electron, weaving the dream of the world. We have traveled far in our search for the ghost. We have seen it as a cloud filling a stadium, as a point piercing the void, and as a thread weaving the tapestry of the cosmos. We have seen it spinning in the dark and holding hands with its twin across the universe. But in all these places the electron was still moving. It was vibrating with the heat of existence. It was buzzing with the energy of the room, the light of the stars, the chaotic thermal dance that we call temperature. Tonight, we are going to stop the music. We are going to descend into the deepest, quietest basement of the universe. We are going to a place colder than the space between the galaxies, colder than the void. We are going to the edge of absolute zero. And here, in this freezing silence, we are going to see the electron do something that defies everything we have learned so far. We are going to see it surrender its most precious possession, its identity. We are going to see the size of the particle dissolve into the size of the collective soul. Imagine we are in a laboratory, but this is not a normal lab with beakers and fires. It is a place of lasers and magnetic traps, a place designed to create a stillness so profound it feels unnatural. We take a cloud of atoms, maybe rubidium or sodium. Inside each of these atoms, our electrons are whizzing around their nuclei, trapped in their orbitals, defining their little clouds of probability. At room temperature, these atoms are like billiard balls. They are bouncing off each other, hitting the walls, chaotic and individual. They have high energy. They have short wavelengths. They are distinct. You can point to one and say, that is atom A, and point to another and say, that is atom B. But now we begin to cool them down. We use lasers to push against them, slowing their motion. It is like spraying water on a runner to slow him down. We drain their energy. We drain their heat. The temperature drops. It goes down to freezing, then down to the temperature of liquid nitrogen, then down to the temperature of deep space, 3 Kelvin. But we don't stop there. We go lower. We go down to microkelvin, nanokelvin. We get to within a billionth of a degree of absolute zero. And as the cold takes hold, a strange transformation begins. Remember Heisenberg. Remember the rule. If you know the momentum, you don't know the position. As we cool the atoms, we are robbing them of their momentum. We are bringing them to a near halt. We know their speed very precisely. It is almost zero. So What happens to their position? It becomes infinitely uncertain. The cloud of the atom begins to grow. The fuzziness expands. At room temperature, the atom was a tiny speck. But now, in the extreme cold, its wave function starts to swell. It gets bigger and bigger. It becomes a fuzzy blob that is larger than the distance between the atoms. Imagine a crowd of people in a room. At first, they are all running around, distinct individuals. But as they slow down, they start to melt. Their boundaries expand. They turn into ghosts that overlap. Suddenly, at a critical temperature, a phase transition occurs. The expanding waves of the individual atoms touch. They overlap. And in a flash of quantum magic, they snap together. They lose their individual wave functions. They merge into a single, giant wave function. They become a Bose-Einstein condensate. They are no longer a million separate atoms. They are one single superatom. It is as if the crowd of people suddenly dissolved and became a single, giant ocean of consciousness. Now, look at the electrons inside this condensate. Usually electrons are fermions. They are antisocial. They refuse to share the same state. They resist this kind of merger. This is the Pauli exclusion principle we talked about, the force that keeps matter solid. But in the extreme cold, under the right conditions, even the stubborn electrons can be tricked. In certain materials, when it gets cold enough, an electron moving through the crystal lattice pulls the positive ions toward it slightly. This creates a ripple of positive charge. A second electron, attracted to that positive ripple, follows the first one. They form a pair, a Cooper pair, and this pair, this marriage of two antisocial electrons, behaves like a boson. It behaves like a social particle. Suddenly, the rules of exclusion vanish. The police are gone. The Cooper pairs can now condense. They can all fall into the lowest energy state together. They can merge. They become a superconductor. In this state, the electrons stop bumping into things. They stop experiencing resistance. They stop having individual collisions. They move as one vast flowing army. If you start a current flowing in a loop of superconducting wire, the electrons will march forever, without a battery, without a power source. They will just keep flowing round and round for the age of the universe, never losing energy, never slowing down. They have become a perpetual motion machine of the quantum world. But let us ask our question. How big is the electron now? In a superconductor or in a Bose-Einstein condensate, the question loses its meaning entirely. The electron is no longer a localized object. The wave function of the Cooper pairs extends through the entire wire. If the wire is a mile long, the size of the electron state is a mile long. We have taken the microscopic and made it macroscopic. We have dragged the quantum ghost out of the basement and put it on the table where we can see it. There are videos of Bose-Einstein condensates forming. You can see a fuzzy cloud on a monitor snap into a sharp peak. That peak is a single quantum object, big enough to see with a magnifying glass. It is a visible ghost. This tells us something profound about the nature of size. Size is a property of separateness. Things only have size because they have edges, because they end where something else begins. I end at my skin. You begin at yours. The air ends at the wall. But in the condensate, there are no edges. There is no me and you. There is only us. When the identity dissolves, the boundaries dissolve. And when the boundaries dissolve, size becomes infinite within the system. The electron, that tiny point we searched for, is revealed to be a fluid. It is capable of merging with its brothers and sisters to form a river of light that flows without friction. This is the state of matter that is closest to pure silence. It is the stillness of the mind when thoughts cease. In the chaos of our daily lives, we are like the hot atoms. We bounce off each other. We have sharp boundaries. We defend our personal space. We feel the repulsion of the Pauli principle in our social interactions. But in the deep cold of meditation, or in the moments of profound connection, we cool down. Our boundaries soften. Our wavelengths expand. We touch the people around us, not with skin, but with empathy. We begin to overlap, and for a moment, we feel what it is like to be a condensate, to be part of a whole that is greater than the sum of its parts. The electron knows this state. It is waiting for the cold to set it free from the prison of individuality. But the universe is rarely this cold. Most of the universe is hot, violent, exploding. We live in a rare, warm epoch between the fire of the Big Bang and the ice of the heat death. So, the electron is usually forced to be an individual. It is forced to be a point. But the memory of the condensate is always there, hidden in the physics. Now, we must leave the cold. We must turn the dial the other way. We have seen what happens when we freeze the ghost. It grows. It merges. But what happens if we heat it up? What happens if we pump so much energy into the electron that we approach the limits of physics itself? We are going to travel back in time, back to the beginning, back to the first fraction of a second after the Big Bang. In that primordial fire, the rules of size and mass were different. We are going to ask, what is the smallest a thing can possibly be? We are going to hit the hard floor of the universe, the pixel size of reality. We are going to talk about the Planck length. Is the electron smaller than a Planck length? If space is pixelated, if it is made of tiny, discrete chunks of geometry, can an electron fit inside one pixel? Or is the electron a knot tied using the pixels? We are leaving the smooth ocean of the field and entering the geometric desert of quantum gravity. The silence of the cold is behind us. The roar of the beginning is ahead. But before we go, take one last look at the condensate. Visualize that perfect, shimmering drop of superatom. A billion hearts beating as one. A billion electrons singing the exact same note. It is the most perfect thing in the universe. A flaw in the chaos. A glimpse of unity in a world of separation. The size of the electron is the size of the love that binds it. And in the cold, that love is infinite. We have stood in the absolute silence of the frozen condensate, where the electron surrendered its identity to the collective soul. We have seen the boundaries of the self dissolve into a single, shimmering wave of unity. But now, we must break the spell. We are going to turn the dial of the universe in the opposite direction. We are going to leave the peace of the cold and travel into the heart of the fire. We are going back to the beginning. Imagine we are rewinding the cosmic clock. The stars are flying apart in reverse, collapsing back into gas clouds. The galaxies are rushing toward each other, merging, spinning faster and faster. The universe is shrinking. As it shrinks, it gets hotter. The gentle microwave background radiation becomes a blinding white light, then a searing gamma-ray fire. We pass the moment when the first atoms formed. We pass the moment when nuclei could hold together. We are back in the primordial soup, a plasma so hot and so dense that matter and energy are indistinguishable. But we do not stop there. We go deeper. We go back to the first fraction of a second, to a time when the entire observable universe was squeezed into a space smaller than a single atom. Here, the rules of the game change again. In this crushing density, we are forced to ask the ultimate question about size. We have been asking, how big is the electron? And getting evasive answers, a cloud, a point, a thread. But now we ask, Is there a limit? Is there a bottom to the rabbit hole? Can you keep dividing space forever? Can you take a slice of space and cut it in half, and then cut that half in half, infinitely, forever? The ancient Greeks wrestled with this. Zeno asked if an arrow could ever reach its target if it had to cross half the distance, then half of the remaining distance, and so on. In our comfortable, everyday world, space feels smooth. It feels continuous. You can glide your hand through the air, and it doesn't click or stutter. It feels like perfect seamless fluid. But physics tells us that if we go small enough, smaller than the atom, smaller than the proton, smaller than the point where our current math breaks down, we hit a hard floor. We hit the pixel size of reality. We call this the Planck length. It is a number so small that it mocks the human imagination. It is 1.6 times 10 to the power of minus 35 meters. To understand how small this is, imagine we take a single atom of hydrogen. We blow it up until it is the size of the entire observable universe, billions of light years across. In that universe-sized atom, the Planck length would be the size of a single tree. This is the grid of the cosmos. This is the resolution of the screen on which the movie of reality is played. And here lies the great crisis of the electron. We have said repeatedly that the electron is a point particle. A point has zero dimension. Zero is smaller than the Planck length. But if space itself is pixelated, if there is no such thing as a distance smaller than a Planck length, then how can an electron be a point? An electron cannot fit between the pixels. There is no between. So, either the electron is exactly 1 pixel in size, or our understanding of points is a lie. This brings us to the most violent conflict in all of physics, the war between quantum mechanics and gravity. Quantum mechanics, the theory of the electron, loves points. It assumes space is a smooth stage where particles can dance. General relativity, Einstein's theory of gravity, says that space is not a stage, but a fabric that bends and curves. Mass tells space how to curve. Now, imagine our electron. It has a tiny mass, but if you squeeze that mass into a point of zero size, the density becomes infinite. Infinite density means infinite gravity, infinite curvature. According to Einstein, a point with mass should punch a hole in the universe. It should wrap space around itself so tightly that it creates a tiny black hole. So, logically, every electron in your body should be a microscopic black hole. But if electrons were black holes, they would evaporate in a flash of Hawking radiation. They would be unstable. They would vanish. And yet, the electron is the most stable thing we know. It never decays. It never dies. So, we have a paradox. The point theory breaks the universe. To solve this, physicists had to dream up a new shape for the electron, a shape that respects the pixel size of the universe. They had to invent string theory. Imagine we zoom in on our electron. We zoom past the cloud, past the uncertainty, past the field. We get down to the Planck scale, and suddenly the point resolves into something else. It is not a dot. It is a loop. It is a tiny, vibrating loop of energy, a rubber band made of pure existence. This loop has a size. It is roughly the size of the Planck length. It is 1 pixel wide. Because it has a size, because it is not zero, it does not create a singularity. It does not punch a hole in space. It smears its mass out just enough to save the universe from collapsing into black holes. This theory suggests that the electron, the quark, the photon, all the different particles in the zoo of reality, are actually the same thing. They are all made of the same strings. The only difference between an electron and a quark is the way the string vibrates. It is like a violin string. If you pluck it one way, it plays an A note. If you pluck it another way, it plays a C note. The electron is just a specific note played on the strings of the cosmos. Mass is the pitch of the note. Charge is the volume. Spin is the timbre. We are back to the music. We are back to the idea that the universe is a symphony. But this symphony is playing on a stage that is terrifyingly chaotic. At the Planck scale, space is not empty. It is not quiet. It is what John Wheeler called the quantum foam. Imagine you are flying over the ocean in a storm. From high up, the waves look smooth, but down low, the water is churning. It is full of bubbles, crashing spray, and violent turbulence. At the Planck scale, space and time themselves are churning. Up and down lose their meaning. Before and after get tangled. Wormholes open and close in a trillionth of a second. Dimensions curl up and unfurl. It is a boiling cauldron of geometry. And our electron, our tiny vibrating string, is navigating this storm. It is buffeted by the waves of the foam. It is surfing on the turbulence of geometry. This changes our question of size into something even stranger. If space itself is boiling and changing size constantly at the smallest scale, then the size of the electron is fluctuating too. It is breathing. It is expanding and contracting with the rhythm of the foam. But string theory demands a price for this elegance. It demands room. A violin string needs air to vibrate. It needs space to move. The strings of the electron need space too, but 3 dimensions, up, down, left, right, forward, backward, are not enough. The math of the vibrations gets tangled in 3 dimensions. The notes sound wrong. To make the music work, the electron needs more room. It needs 6 more dimensions. String theory suggests that our universe is not 3-dimensional. It is 10-dimensional, or 11, depending on who you ask. But where are these other dimensions? We don't see them. We can't move into them. The theory says they are curled up. Imagine a garden hose lying on the ground. From an airplane, it looks like a 1-dimensional line. You can only run back and forth along it. But if you are an ant crawling on the hose, you realize there is a 2nd dimension. You can walk around the circumference of the hose. The extra 6 dimensions are like that circumference. They are curled up into tiny loops, smaller than an atom, smaller than the electron. They are curled up at the Planck scale. So, the electron string is not just vibrating in our familiar space. It is vibrating around these tiny, hidden dimensions. It is wrapping itself around the geometry of the invisible. The specific shape of these curled-up dimensions, the way the hose is twisted, determines the vibration of the string. It determines the properties of the electron. Why does the electron have the mass it has? Why does it have the charge it has? Because of the shape of the 6 invisible dimensions it is dancing in. This means that the fundamental nature of matter, the very building blocks of your body, depends on the geometry of a hidden world we can never see. You are made of geometry. You are made of the shape of nothingness, vibrating in dimensions that are folded away from your perception. The size of the electron is the size of this hidden world. It is the size of the knot that ties the dimensions together. This is a beautiful, heady idea. It solves the gravity problem. It unifies the forces. It turns physics into music and geometry. But there is a catch. We have never seen a string. We have built the Large Hadron Collider, a machine 17 miles around, to smash particles together and look for these strings, or for the extra dimensions. We have looked for the energy to leak away into the hidden dimensions. We have looked for the echoes of the strings, and so far, silence. The electron, when we smash it, still looks like a point. It refuses to reveal its stringy nature. It refuses to show us the extra dimensions. We are stuck at the gate. We have a beautiful map, string theory, but we cannot see the territory. Maybe the strings are there, but they are just too small for us to ever see. Maybe the Planck length is a wall we can never climb over. Or maybe, just maybe, we are wrong again. Maybe the universe is not made of strings. Maybe it is made of something even more abstract. Maybe it is made of information. There is a growing suspicion in physics that space and size are not fundamental at all, that they are illusions, like the heat in a room is just an illusion created by moving atoms. Maybe space is a hologram. Imagine a hologram on a credit card. It is a flat, two-dimensional surface. But when you shine light on it, a 3D image pops out. The 3D world is encoded on a 2D surface. Some physicists believe that our entire three-dimensional universe, with all its depth and stars and galaxies, is just a projection. A projection from where? From a distant, two-dimensional surface at the edge of the universe. In this view, the electron in your finger is not a solid ball or a string or a cloud. It is a bit of data, a treasure or a one encoded on the boundary of the cosmos. The size of the electron is just the resolution of the projection. It feels 3D to us because we are inside the hologram. We are part of the projection. But the real electron is just information written on the cosmic horizon. This idea, the holographic principle, comes from studying black holes. It suggests that the amount of information in a volume of space is determined not by the volume, but by the surface area surrounding it. If this is true, then size is the ultimate illusion. There is no inside the stadium. There is only the surface of the stadium, painting the picture of the inside. We are getting dizzy now. The ground is gone. The dimensions are curled up. The strings are vibrating. The hologram is shimmering. We started by asking, how big is the electron? Hoping for a number, hoping for a simple measurement in meters or inches. Instead, we have found that size dissolves when you look at it too closely. It dissolves into probability. It dissolves into entanglement. It dissolves into geometry. It dissolves into information. The electron is a shapeshifter. It wears the mask that the universe needs it to wear. When we need atoms to be solid, it wears the mask of the cloud. When we need to calculate paths, it wears the mask of the point. When we need to understand gravity, it wears the mask of the string. It is the ultimate actor. But what lies behind the mask? Is there a true electron underneath all the theory? Or is the electron just a story the universe tells itself? We are approaching the end of our journey. We have one more place to go. We have looked at the electron from the outside, measuring it, trapping it, theorizing it. But we have not looked at it from the inside. We have not asked what it feels like to be an electron. Does it have an inner life? Does it have a rudimentary form of experience? We are going to step into the dangerous waters of Pansychism. We are going to ask if consciousness is not something that happens to atoms, but something that comes from atoms. If the electron is the building block of your brain, and your brain is conscious, is there a spark of proto-consciousness in the electron itself? Is the silence of the electron actually a form of listening? We are going to close the loop between the physics of the small and the mystery of the mind. The fire of the Big Bang is fading behind us. The pixelated foam of the Planck scale is beneath us. We are floating in a universe made of information, music, and light. And we are about to ask if the light is watching us back. We have traveled to the edge of the universe and back. We have journeyed into the frozen silence of the absolute cold, and the fiery chaos of the Big Bang. We have seen the electron as a cloud, a point, a string, and a wave. We have measured it with rulers of light and weighed it with fields of snow. But in all this searching, in all this measuring, there is one thing we have left out. One variable we have ignored. You, not your body, not the carbon and water that makes up your skin, but the you that is looking out from behind your eyes right now, the you that is hearing these words, the you that feels the weight of the phone in your hand and the wonder in your heart. We have described the electron as an object, a thing out there, a tiny gear in the machine of reality. But the machine has woken up. The machine is aware. And this brings us to the deepest, most uncomfortable, and most beautiful mystery in all of science. It is called the hard problem of consciousness, and it forces us to ask a question that changes the definition of the electron entirely. Is the electron just a building block of matter, or is it also a building block of mind? Let us look at the machinery of your brain. It is by far the most complex object in the known universe. Inside your skull, floating in a dark, quiet bath of fluid, sits a 3-pound lump of wet, gray tissue. It contains roughly 86 billion neurons. Each of those neurons is connected to thousands of others, creating a network of trillions of connections. And what is running through this network? What is the spirit that animates this machine? It is the electron. Every thought you have ever had is a cascade of electrons. When you see the color red, a photon hits your eye, knocks an electron into a higher orbit, and triggers a chain reaction. An electrical signal, a wave of ions moving across membranes, travels down the optic nerve. This signal is orchestrated by the movement of electrons. When you remember your first kiss, or the smell of rain, or the sound of your mother's voice, that memory is encoded in the strength of connections between neurons, connections that are built and maintained by the electromagnetic forces of electrons. When you decide to move your finger, a storm of electrical activity sweeps across your motor cortex, driven by the flow of charged particles. From a physicist's perspective, your brain is just a very complicated toaster. It is a machine that processes energy. It takes in oxygen and glucose, burns them to release electrons, and uses those electrons to push signals around a circuit. But a toaster does not feel love. A toaster does not feel fear. A toaster does not wonder about its place in the universe. You do. So, how does it happen? How do you get feeling out of stuff? How do you take a pile of dead, mindless atoms, carbon, hydrogen, nitrogen, oxygen, and arrange them in a certain way so that suddenly they wake up? If I give you an electron, you will agree it is not conscious. It is a particle. It has mass, charge, spin. It does not have hope or anxiety or the sensation of the color blue. If I give you 2 electrons, they are still not conscious. If I give you 1 billion electrons, they are still just a pile of particles. At what number does the magic happen? At what precise moment does the pile become a person? This is the hard problem. And the standard answer of modern science is, we don't know. Most scientists assume that consciousness is an emergent property. They think it is like a traffic jam. A single car is just a car. But if you put enough cars together on a highway, you get a traffic jam. The jam is a real thing, but it is made of cars. They think consciousness is like wetness. A single water molecule is not wet. But put trillions of them together, and you get wetness. So, they say, the electron is dead, the atom is dead, but the pattern is alive. But there are others, serious physicists and philosophers, who think this is wrong. They think you cannot get mind out of no mind. You cannot get something out of nothing. If the electron is totally zero in terms of experience, then a billion times zero is still zero. So, they propose a radical alternative. They propose that the electron is not dead. They propose that the electron, and perhaps every fundamental particle in the universe, has a tiny, rudimentary, primitive form of inner life. This view is called Pansychism. It does not mean the electron is sitting there thinking about philosophy. It does not mean the electron has a personality or memories or a complex self. It does not know it is an electron. It means that the electron has a spark of experience, a tiny, irreducible hum of existence. Think of it like a pixel on a screen. A single pixel cannot show you a movie. It can only be red or green or blue. It has a very simple state. But if you put millions of pixels together, you can create the image of a face, a sunset, a tragedy, a comedy. The complex picture emerges from the combination of simple pixels, but the pixels must have the capacity to be light. You cannot make a movie out of pixels that are totally dark. In this view, the size of the electron is the size of the smallest unit of consciousness. It is the pixel of the soul. And the you that you feel, the rich, complex, panoramic experience of being human, is the combined symphony of trillions of these tiny electron sparks singing together in the cathedral of your brain. This sounds like poetry, or perhaps mysticism. But there are physicists who are trying to turn this into rigorous science. Sir Roger Penrose, a Nobel Prize winner and one of the greatest mathematical physicists of our time, has teamed up with an anesthesiologist named Stuart Hameroff to propose a theory called orchestrated objective reduction, or ORC, O-R. They suggest that the brain is not just a computer, it is a quantum orchestra, and the instrument being played is the electron. Inside the neurons of your brain, there are tiny structural tubes called microtubules. They are the scaffolding of the cell. For a long time, biologists thought they were just structural, like the bones of the cell. But Penrose and Hameroff suggest that these microtubules are actually quantum isolation chambers. They argue that inside these tubes, electrons are protected from the noisy environment of the brain. They are allowed to enter a superposition. They become ghosts. They exist in multiple states at once. They float in a cloud of probability, just like the electrons in our stadium. And as these superpositions grow, as more and more electrons entangle within the microtubules, the bubble of quantum possibility expands. Eventually, it gets too big. Gravity tears it apart. The universe forces it to decide. The wave function collapses. And here is the magic key. Penrose suggests that this collapse, this moment when the electron snaps from possibility to reality, is not just a mathematical random event. He suggests that the collapse is a moment of consciousness. Every time a wave function collapses, a tiny bing of experience occurs, a spark of awareness flashes in the dark. In a rock or a cloud of gas, these collapses happen randomly and disjointedly. It is just noise. It is a chaotic static of tiny proto-feelings that never add up to anything. But in the brain, the microtubules orchestrate the collapse. They synchronize millions of electrons to collapse at the exact same moment. It is like a conductor raising a baton. Millions of scattered notes are suddenly pulled together into a single massive chord. That chord is your moment of now. 40 times a second, roughly, these synchronized collapses ripple through your brain. 40 times a second, the universe snaps into focus for you. Your stream of consciousness is not continuous. It is a series of quantum sparkles happening so fast that they blur into a feeling of smooth existence. You are a movie played at 40 frames per second, and each frame is a massive, orchestrated collapse of electron wave functions. If this theory is true, and it is still very controversial, still on the bleeding edge of science, it changes everything about how we answer the question, how big is the electron? It means the electron has two sides. It has an external side, the side we measure with our rulers and voltmeters. This side has mass, charge, spin, and position. It is the matter side. But it also has an internal side, a side we cannot measure from the outside. This internal side is the capacity to experience. It is the raw material of feeling. The size of the electron's internal world might be simple, but it is real. It suggests that the universe is not made of dead stuff. It suggests that the universe is made of felt stuff. It suggests that being is just as fundamental as doing. Think about the implications of this. When you look at a star, you're usually thinking about the nuclear fusion, the heat, the gravity. But if every electron in that star carries a spark of proto-consciousness, then the star is a roaring ocean of experience. Not a mind like yours. It has no brain to organize the sparks, but a vast, chaotic sea of being. When you touch the table, the electrons in your finger and the electrons in the wood are pushing against each other. If Pansychism is right, that interaction is not just a mechanical exchange of forces. It is a meeting of experiences. The universe is humming with an internal monologue that we can never hear because we are trapped inside our own specific frequency of consciousness. This perspective heals the final separation. We often feel like strangers in the universe. We feel like we are ghosts in the machine, spirits trapped in bodies of meat, walking through a dead, indifferent world of rocks and gas. We feel that our consciousness is a fluke, a lucky accident of evolution that happened on one obscure planet. But if the electron itself carries the seed of mind, then we are not accidents. We are the natural expression of the universe's fundamental nature. We are what happens when the universe organizes its basic building blocks into a mirror. We are the universe waking up to itself, using the very same particles that make the rocks and the stars. The electron in your brain is the same as the electron in the stone. The difference is only in the arrangement. The difference is in the music, not the instrument. So, how big is the electron? It is big enough to hold the seed of a thought. It is big enough to be the pixel of a dream. It is big enough to be the bridge between the physics of the dead and the mystery of the living. Let us return to the silence for a moment. Close your eyes. Listen to the quiet in the room. But listen deeper. Listen to the quiet inside your own head. Watch your thoughts arise. Watch the feeling of being you. According to the quantum consciousness hypothesis, that feeling is a quantum phenomenon. It is the hum of the vacuum. It is the dance of the microtubules. It is the synchronized collapse of billions of electron clouds snapping into reality, creating the movie of your life. You are not observing the quantum world from the outside. You are the quantum world. You are the event horizon where probability turns into experience. This makes the electron precious. It is not just a speck of dust. It is a carrier of the light. And it raises one more terrifying and wonderful question. If the electron carries this spark, and if the electron is eternal, what happens to the spark when the pattern dissolves? When the body dies, the electrons do not disappear. We know this. They are stable. They last forever. They drift away. They enter the soil, the air, the water. They become parts of trees, parts of other people, parts of the atmosphere. Does the pixel retain any echo of the movie it was part of? Does the electron remember being you? Physics says no. Physics says electrons are indistinguishable. You can wash the slate clean. But quantum mechanics is strange. Information is never truly lost. Is it possible that the entanglement, the deep, invisible connection we discussed in the last chapter, preserves a record? Is it possible that the universe remembers everything, woven into the subtle correlations between the particles that once made us up? We are drifting now into the realm of pure speculation. We have left the solid ground of the laboratory far behind. But that is what the electron does to us. It invites us to the edge. It starts as a dot in a textbook, and it ends as a question about the soul. In the next chapter, we are going to pull back. We are going to zoom out to the very end of time. We are going to look at the ultimate fate of the electron. We know it is stable. We know it does not decay like other particles. But will it last forever? Will the electron survive the death of the universe? Will it be the last witness to the final darkness? We are going to travel to the era of the black hole era and beyond, to the great heat death. And we will see that the electron, this tiny, spinning, feeling, weaving ghost, might be the only thing that remains when the lights finally go out. It is the protagonist of the cosmic story, from the first second to the last. Are you ready to see the end of the world? We have now reached the twilight of the gods. We have followed the electron from the womb of the Big Bang, through the fiery forges of the first stars, into the intricate machinery of the atom, and finally into the mysterious, shimmering cathedral of the human brain. We have seen it build the world, hold up the floor, weave the web of space, and perhaps even light the spark of the soul. But every story has an ending. Or does it? Tonight, we are going to travel forward, far forward. We are going to leave the comfortable warmth of the present day. We are going to speed up the clock of the cosmos. Watch as the sun swells into a red giant and swallows the earth. Watch as it sheds its outer layers and shrinks into a white dwarf, a diamond the size of a planet, held up, as we know, by the stubborn refusal of electrons to share their space. Watch as the other stars in the sky flicker and die, one by one. The blue giants explode, the yellow suns fade, the red dwarfs, those miserly hoarders of fuel, burn for trillions of years, but eventually even they run out of hydrogen. The lights go out. The party is over. The universe enters the degenerate era. It is populated only by the corpses of stars, white dwarfs, neutron stars, and black holes. But we must go further. We must go to a time when even the corpses rot. There is a theory in physics, unproven but widely believed, that the proton is not immortal. The proton, the heavy marble at the center of our stadium, the anchor of the atom, might eventually fall apart. It is a complex object made of 3 quarks, and in the very, very long run, quantum mechanics suggests that these quarks might reshuffle. If this happens, the proton will decay. It will burst apart into a positron and a pion. The half-life of a proton is estimated to be at least 10 to the power of 34 years. That is a 1 followed by 34 zeros. It is a time span so vast that if you counted every grain of sand on Earth, and for each grain you weighted the entire age of the current universe, you would not even have started to scratch the surface of this number. But eternity is long, and eventually the clock strikes. Imagine a universe where the atoms themselves begin to die. The matter that makes up the planets, the asteroids, the dead stars, it all begins to dissolve. The protons decay, the nuclei shatter, and what is left? The electron. The electron is different. The electron is a lepton. It is a fundamental particle. It is not made of quarks. It has no smaller parts to decay into. There is a law in the universe called the conservation of charge. It says that electric charge cannot just disappear. It has to go somewhere. The electron carries the fundamental unit of negative charge. For it to decay, it would have to turn into a lighter particle with the same charge. But there is no lighter particle with the same charge. The electron is the bottom of the ladder. It is the lightest charged object in existence. It is stuck. It is immortal by necessity. So, as the protons dissolve and the neutrons vanish, the electrons are cast adrift. They are evicted from the stadiums they have inhabited for aeons. The nucleus is gone. The orbital is gone. The atom is gone. The electron is now a lonely wanderer in an expanding, empty void. This is the dark era of the universe. The black holes will eventually evaporate, as Stephen Hawking predicted. They will spew out their mass in a slow trickle of radiation until they pop and vanish, and then there will be nothing left but a thin soup of particles, photons, neutrinos, and our hero, the electron. Navigating this endless night, the electron faces a crisis of size that makes all our previous questions look trivial. In the vacuum of the far future, the universe has expanded to incomprehensible dimensions. The galaxies are ripped apart. The distance between individual particles is measured in light years. An electron floating in this void interacts with nothing. It sees no light. It feels no gravity. It touches no other fields. Without interaction, what happens to the wave function? Remember the cloud. The electron is a wave of probability. When it is trapped in an atom, the cloud is confined. It is the size of a stadium. But when it is free, when there are no walls, the wave function spreads. It spreads and spreads and spreads. Over trillions of years, the wave function of a single lonely electron could expand to become the size of a galaxy. It could become the size of the current observable universe. The electron is no longer a point. It is a whisper, a faint, ghostly mist that covers billions of parsecs. It is everywhere and nowhere. Its size is effectively infinite. And yet, it is still a single entity. It still carries that one unit of charge, smeared out over the darkness. It still carries that spin 1-2, that twist in the fabric of reality. It is a ghost haunting the corpse of the cosmos. But is it truly alone? Remember the proton decay. When a proton dies, it produces a positron, the anti-electron. So, for every surviving electron in the dark era, there is a surviving positron somewhere out there. They are enemies, they are lovers, they are matter and antimatter. If they touch, they annihilate. They turn into pure light. In this vast, expanding void, the chances of them meeting are infinitesimally small. They are needles in a haystack the size of infinity. But eternity is a long time. Slowly, over time scales that defy mathematics, 10 to the power of 100 years, 10 to the power of 1,000 years, their paths might cross. The electrostatic force, the force that we felt in our finger in Chapter 1, still works. It has infinite range. The negative electron and the positive positron will feel a tiny, tiny tug across the void, a call across the deep. They will begin to spiral toward each other, but because the universe is expanding so fast and because they are moving so slowly, this dance takes forever. They might form an atom, a strange, final atom called positronium. No nucleus, no heavy marble in the center, just the electron and the positron orbiting each other in the dark. But this orbit is huge. Because they are moving so slowly, the atom they form could be larger than our current galaxy. Two tiny ghosts, holding hands across a distance of 100,000 light-years, bound by the memory of a force that once held the world together. They spiral in, closer, closer. The spiral takes trillions of years. And then, finally, the kiss. They touch. Flash. 2 photons of gamma rays streak out into the darkness. The electron is gone. The positron is gone. The mass is converted back into energy. The last knot is untied. The last thread is cut. This is the final death. But wait. Will they all find each other? The universe is expanding acceleratingly. The space between particles is growing faster than light. It is very likely that some electrons will be separated from their partners forever. They will be pushed apart by dark energy faster than the call of love can pull them together. These electrons will be truly alone. They will drift forever, isolated, frozen, their wave functions stretching thinner and thinner until they become almost indistinguishable from the vacuum itself. They will be the eternal witnesses. If the universe ends in a big freeze, a state of maximum entropy, the electron will be the last structure to survive, long after the black holes have evaporated, long after the light has faded, long after the concept of time has lost its meaning because nothing ever changes anymore. The electron will be there, a tiny spinning point of angular momentum, a seed of charge, a spark of potential that can never be realized because there is nothing left to realize it with. This is a melancholic thought. It makes us feel the crushing weight of the void. But there is a strange beauty in it, too. It means that the universe does not end in 0. It ends in 1. It ends with a survivor. And if we embrace the ideas from the last chapter, the idea that the electron carries a spark of proto-consciousness, then the end of the universe is not absolute darkness. There is still a feeling there, a hum, a solitary note playing in the cathedral of the void. It is the hum of the electron, remembering the stars, remembering the time when it was part of a sun, remembering the time when it was part of a leaf, remembering the time when it was part of a brain that wondered, how big am I? The electron carries the history of the universe in its spin. But there is one loophole, one trap door in the floor of the universe that could change everything. We assume the electron is stable because it is the lightest charged particle. But what if our definition of mass changes? Remember the Higgs field, the snow, that gives the electron its mass. Some physicists believe that the Higgs field might be metastable. This means that the current state of the vacuum, the current thickness of the snow, is not the deepest possible state. It is like a ball sitting in a valley. But there is a deeper valley further down the hill. If, by some quantum accident, a part of the universe tunnels through the hill and finds the deeper valley, a bubble of true vacuum would form. In this bubble, the laws of physics would change. The constants of nature would be rewritten, and the mass of the electron would change. If this bubble expands, and it would expand at the speed of light, destroying everything in its path, it would overtake the drifting electrons. Suddenly, the electron might find itself heavy, or weightless, or unstable. In the true vacuum, the electron might finally decay. It might dissolve into something else, something we cannot imagine. This is called vacuum decay. It is the ultimate cosmic catastrophe. And if it happens, then even the electron is mortal. Even the ghost will eventually die. But we do not know if this will happen. For now, our best mathematics says the electron is the king of survival. It is the atlas that carries the sky, and it will continue to carry it long after the sky is empty. So, how big is the electron? In the end, it is big enough to outlast God. It is big enough to be the period at the end of the sentence of existence. We have almost reached the end of our journey. We have seen the electron in the past, the present, and the deep future. We have seen it as a builder and a destroyer, a wave and a particle, a lover and a hermit. But there is one final step we must take. We must bring the electron back home. We must take all these vast, terrifying, beautiful concepts, the stadium, the cloud, the string, the multiverse, the consciousness, the heat death, and we must put them back into your finger. We must answer the question we started with. What does it mean to touch? We need to close the circle. We need to integrate the mystery into the mundane. In the final chapter, we will wake up from this dream of science. We will look at the world with new eyes. We will understand that the size of the electron is not a number. It is a feeling. It is the feeling of being alive in a universe that is far stranger, far softer, and far more interconnected than we ever dared to hope. The journey is almost over. The silence is waiting for the final word. Are you ready to come back to the world of the living? We have arrived at the end of our descent. We started this journey with a simple, almost childlike question. How big is an electron? It felt like a question that should have a number for an answer. We expected to find a tiny marble, a speck of dust, something we could measure with a very fine ruler. We expected the universe to be made of things, little hard nuggets of reality that stack together like Lego bricks to build the world. But the universe, as we have discovered, is not made of things. It is made of music. It is made of ghosts. It is made of relationships. We found that the electron is a cloud the size of a stadium, a point the size of nothing, a ripple in an infinite ocean, a knot in a 10-dimensional string, and a spark of proto-consciousness. We found that it is everywhere and nowhere, identical to its brothers, entangled with its distant lovers, and destined to survive the death of the stars. But now, I want you to open your eyes. I want you to leave the laboratory of the mind. I want you to leave the particle accelerators and the black holes. I want you to look at your hand again. Place it back on the surface in front of you, the table, the chair, the screen. Do it now. Press your finger down. Feel that pressure? That is no longer just a sensation. It is a symphony. When you started this story, that pressure was just touch. Now, you know what it really is. It is the roar of the Pauli exclusion principle. It is the sound of trillions of electrons in your skin screaming no to the trillions of electrons in the table. It is the stubbornness of the fermion, refusing to share its quantum state, creating the miracle of solidity out of the vacuum. Without that refusal, your hand would pass through the table like smoke. You would fall through the floor toward the center of the earth. The earth would collapse into a tiny, dense nugget. The fact that you can sit here, supported, safe, solid, is a gift from the electron spin. Now, look at the color of your skin. Look at the light reflecting off the table. What is that light? It is the dance of the electron. Light is generated when an electron drops from a high shelf in the atomic stadium to a low shelf. It sheds its excess energy as a photon. Light is absorbed when an electron catches a photon and jumps up to a higher shelf. Every color you have ever seen, the blue of the sky, the green of the grass, the red of a rose, the face of someone you love, is a message sent by an electron. The electron is the painter of the universe. It is the bridge between matter and light. And what about the warmth you feel? That is the electron too. It is the vibration of the atoms, the kinetic energy of the clouds bumping into each other, transferring heat, keeping you alive. We have spent 10 chapters looking for the size of the electron, and the answer finally is this. The electron is the size of your life. It is not a dot in the distance. It is the very fabric of your experience. The electron is the ink in which the story of reality is written. And this brings us to a profound realization about our place in the cosmos. We often feel small. We look up at the night sky, at the Milky Way stretching across the dark, and we feel insignificant. We are just specks on a rock, living for a blink of an eye. But quantum mechanics flips this perspective upside down. If the universe is created by observation, if the wave function only collapses when it interacts, if the electron is a cloud of potential until it meets a partner, then you are not just a spectator. You are the projector. Your consciousness, that spark we discussed in the last chapter, is the needle that knits the world together. Every time you look at a star, you are collapsing its wave function. You are forcing the universe to be specific. You are forcing the electron to decide. You are an essential part of the machinery of existence. Without you, without the observer, the universe might just be a silent, dark fog of probability, waiting for someone to notice it. This is the ultimate answer to the size question. The electron is small. Yes, it is smaller than small, but its purpose is vast. It is the interface. It is the connector. It connects the nuclear fire of the sun to the photosynthesis in the leaf. It connects the chemistry of the ancient ocean to the biology of your blood. It connects the physics of the Big Bang to the philosophy of the human mind. We asked, how big is the electron? The answer is, it is big enough to hold everything that matters. And now, as we close this book of mysteries, I want to leave you with a final image, a meditation to carry with you into your dreams. Imagine you are standing on a bridge. Below you is a river, but it is not a river of water. It is a river of mist, shimmering, glowing, swirling mist. This is the quantum field. This is the ocean of reality. Occasionally, you see a little knot form in the mist, a ripple, a vortex. That is an electron. It lasts for a moment, or 1 billion years, and then it dissolves back into the flow. Now, look at yourself. Look at your hands on the railing of the bridge. You are made of the mist, too. You are a standing wave, a complex, beautiful, temporary pattern that the river has formed. You're not separate from the river. You are the river, curling up into a shape that can look at itself. The electrons in your body are just the water molecules in the wave of you. They will flow on when the wave crashes. They will become other waves. They will become rain and clouds and sea. But for this brief, miraculous moment, they are holding the shape of you. They are holding your memories. They are holding your hopes. They are holding your curiosity. This is the miracle of the mundane. We don't need magic. We don't need dragons or wizards. The fact that an electron exists is magic enough. The fact that a zero-dimensional point can build a cathedral, or a brain, or a star, is the greatest miracle of all. We live in a universe that allows for complexity, a universe that allows for structure, a universe that allows for us. And it does it all with a handful of dust and a few simple rules. So, the next time you feel overwhelmed by the complexity of life or the vastness of the cosmos, remember the electron. Remember its uncertainty. It doesn't know where it is going, and that is okay. Its fuzziness is its freedom. Remember its spin. It has to turn twice to see the truth. Sometimes we do too. Remember its entanglement. You are never truly alone. You are connected to the whole. And remember its silence. Deep down, beneath the noise of your thoughts, beneath the rush of the blood, beneath the chemical burning of the cells, there is a quiet field, a field of infinite potential, That is where you come from, and that is where you are. The journey of the electron is your journey. It is a journey from the simple to the complex, from the fire to the cold, from the lonely point to the connected web. It is a journey of discovery. We have reached the end of our 10 chapters. We have touched the limit of what science can tell us today. Tomorrow, we might learn something new. We might find the string. We might find the fourth dimension. We might find that the electron is something else entirely. That is the beauty of science. It is not a book of answers. It is a book of questions. It is a story that never ends. But for tonight, the story pauses here. The electron is a ghost, and you are the house it haunts. Be a good house. Be kind to your ghosts. They have traveled a long way to be you. Thank you for walking this path with me. Thank you for descending into the small to find the large. If this journey has shifted something in you, if it has made the table feel a little more solid, or the light a little more precious, or the silence a little more profound, then we have succeeded. We have touched the mystery, and the mystery has touched us back. So, tonight, when you lay your head on the pillow, feel the electrons in the fabric pushing against the electrons in your cheek. Feel the support of the universe. Close your eyes, drift into the cloud. Let your boundaries soften, and remember, you are big, you are vast, you are made of stars and silence. Good night, fellow traveler, and keep wondering.